Hello, I hope you can all hear me. Welcome to Thursday. This is day 4 of this conference. Welcome to the Refereed Track talk. Excited to see you all here. And we'll go through an introduction quickly, and then I'll hand it over to Amit. Amit, I need to steal presenter from you again. Sorry.
Sure thing.
Okay, first of all, this wouldn't be possible without our sponsors. We have Facebook as our diamond sponsor. We have IBM as our platinum sponsor. And our gold sponsors are ARM and Microsoft. And our silver sponsors are AWS, Netflix, and Red Hat. Thanks to them as well. And our speaker gift, which is a solo key that I have lying around somewhere here, is by Collabra. It's pretty cool. Thank you for that. And our t-shirt sponsor is VMware. Conference service is provided by Linux Foundation. We've received a lot of help from them, so thanks to Linux Foundation as well. And we have a COC, which you've seen a couple of times before. Please read it. Don't harass anybody. Be sensible. Be kind. You know, the basic things that most people manage quite easily. And if you want to ask a question after or during the presentation, although in the referee track, it's probably better to ask it after the presentation, unless the speaker tells you to do so. Please turn on your microphone and camera when you want to ask a question, and then go ahead. And while the speaker is talking, turn it off. And this is the planning committee. David, our chair, Eleanor, Kate, James, myself, Jonathan, Guy, and Stephen. So thanks to everyone as well. Amazing people. They made this all possible. So, and with that, I'm happy to hand it over to Amit. Amit, I can switch on your presentation if you want.
All right. Can you hear me?
Yes, we can hear.
Okay. Is the poll still up, or did that disappear when you took over presenter? Can anyone see the poll?
I did see the poll and I did vote, so I assume everyone else could as well. But you can put it up again if you want.
If I could only figure out where the settings were, because I don't see a way to get the poll back here. Interesting. Never mind. So thanks all for being here. Good day to all of you. And so I want to talk today about Linux and Zephyr interoperability. I'll come back to the poll midway through the talk, no worries. So at this point, thanks for attending this talk. What I want to think about for this session is whether it makes sense to think of Linux and Zephyr ecosystems as part of a single software stack that could be used to make a continuum of products. So anything that runs on a microcontroller all the way to CPUs. So Zephyr running on microcontrollers, and obviously Linux running on CPUs. The reason being, by increasing the compatibility between the projects and the interoperability between the projects, we can reduce overall burden and make it a lot simpler to build beautiful products. So in the end, the focus of this presentation is around building beautiful products. Let's see if this works. So I don't have presenter here, it seems, Christian, because I'm not able to change the slides. That's the reason I wasn't able to see the poll. Okay, fair enough. Thank you.
Can you switch slides? You can, right?
Yeah, I can. Thank you.
Okay, cool.
So feel free to ask questions at any point. I think we have plenty of time. I shouldn't take more than 30 minutes. You can either speak up or type in the chat, and I'll make it a point to keep an eye out there. So as a bio, I've been involved in Linux for a very long time, and and much less so on the Zephyr side, mostly during its early days, while I was at Linaro. But I'm hoping that'll change with this new thing that I'm working on. I've worked at distro vendors. I've worked with a lot of SoC vendors. I've done a bunch of product development as well. I'm currently heading up a product architecture for a project that is, as of yet, not announced. So more details about that later. I'm not trying to be mysterious. It's just we're not ready to announce the entire thing. People are dotting the I's, crossing the T's, and before an announcement is made. Oops. Okay. So this picture in front of you is a bunch of IoT devices that are available in the market today. So something like a Fitband or a smart camera, a watch, even a rice cooker. Everything has smart attached to it in the front. A lot of it uses Linux. If it's microcontrollers, they use a variety of RTOSes. So there's a huge variety of. I think there's a lot of fragmentation on the RTOS world. There's a lot of different RTOSes in use, but definitely a lot of Linux use. So it's either embedded Linux or some variant of usually some very old variant of Android. And I have four things from these pictures in my house. And in almost every case, the user experience is terrible. The way I onboard things when I buy a new device, to how I interact with the device, to how the device is updated, almost never. So they never receive software updates in a lot of cases, and the applications that are available to control these devices. So in general, terrible experience. And if somebody has more of these devices in their home, please accept my condolences for that very reason. I have a hard time with them. So it is effectively the IoT juggernaut. I mean, there's hundreds and hundreds of these devices being put out every single year by hundreds of companies across the world, big and small. There's not a whole lot of good software architecture in a lot of cases in the firmware and the images that are being loaded onto these products. Fair enough. So if you look at the kernel parts of it, if you look at upstream rather, so both the Linux and the Zephyr projects have nice, smoothly functioning, well-oiled machines as far as LTS releases are concerned. So they have LTS releases. They have a variety of security fixes flowing into these LTS releases because they have dedicated teams that are working through this and backporting stuff into your LTS kernel and whatnot. And I'm going to focus on LTS kernels for this because we are talking products. I haven't seen a lot of products that are shipping mainline, and I don't think it's going to change very soon. So these LTS releases receive a lot of CI testing as well. But if you go out and look for this, I think besides a few Android phones maybe, and a lot of Chromebooks, I don't see a lot of the latest work that goes into the LTS and whatnot being deployed on these devices as updates. So it's very common to, even if you do see an LTS, it's very common for the LTS to be like 6 months old or more. So there's a bunch of open security fixes, and there's a big vector of attack that's still open on these devices, and that's not surprising to anybody. The reason I feel is that a lot of these companies, especially the smaller and medium-sized ones, lack specialists. So specialists who know about things like OTA. So how are my flash partitions laid out, or how should they be laid out? How is my payload created? How do I get the payload onto these devices over the network? How do I recover from bad firmware updates, that sort of thing? There's so many OTA frameworks, especially on the Linux side, that that itself is a big choice. Do I go with something like OS3 or Milena or the update framework or Rauk or something else? Because each of them has their own pros and cons, whether it's a full image update versus deltas versus only application updates like container or something. And interestingly, because a lot of companies are trying to make money of OTA, there's a lot of proprietary cloud components for the OTA solutions. People are trying to monetize by giving away the client side and then monetizing on the server side in the cloud. The next category of specialists is the security specialists. Again, this is a wide gamut. Everything from, okay, what sort of secure boot architecture do I have? Do I use Opti, TFM, or something else, depending on architecture? How do I have processes in place to check for CVEs? Because it's not just the kernel. Remember, it's a bunch of other software around the kernel, your user space. So check for CVEs across all these packages, fixing them, testing them, and then finally deploying the updates across many of these devices. So the next category of specialists are key provisioning specialists. So I just call this out separately from security, mainly because it can happen, it may happen in a separate location outside your development offices. So this might happen on the factory floor where the key lifecycle management starts. So how do you provision a device with keys and so on and so forth? What are the tools for signing? Then there is IP compliance. This has become a hot topic lately. Almost all projects I know about, Linux Foundation, Linux with SPTX, Zephyr, they're all about the software bill of materials, because that's where the supply chains are moving to. Everybody wants to know what am I shipping as part of the product, especially if you're a medical device company or a or automotive vendor, for example. Networking is another one of those things because there's a plethora of protocols. Are we using secure communications? Is it always SSL encrypted in some sense, or are we sending out packets, plain text packets over the air? So again, I'm belaboring a point, effectively saying that there's a lack of specialists in a lot of these companies. And that is leading to what we are seeing in the IoT space today in terms of software quality, in terms of the lack of software quality, so to say. As a quick aside, when I'm working on a product, one thing that keeps me awake at night is Twitter. More specifically, this handle on Twitter, Internet of Shit. If you don't follow it or if you've never seen this, it's a good one to check out. If you follow this handle and avoid all the things that they say you shouldn't be doing, all the things that they're making fun of, I think your product, your product will end up above average. So this actually keeps me awake in terms of, okay, I don't want my product, anything that I've ever worked on, to show up on the Internet of Shit. So what is the path to a product? So two different thoughts. Let's consider the Zephyr path and the Linux path to a product. And we are only focusing on software here. Hardware is a completely different ballgame. So let's just focus on the software aspects of the product at this point. So when talking about Zephyr, what do you get when you download the Zephyr sources? You effectively have support for all the major microcontroller families as part of the code base. The APIs are very nicely documented. There's a lot of sample code for the various frameworks in there. There's out-of-box support for a variety of popular sensors and other hardware out there, peripherals that you might connect to these boards. And it's all fairly well tested in CI, including their documentation, which is generated through their build system. So if you go to the Zephyr website, read their documentation, and it says, connect this sensor to this board this way and run this code, chances are it is going to work, because they've done a very good job of plumbing through that entire process and making sure it's always up to date. One other thing that Zephyr does nicely, and which will be key to the discussion further down the line, is that they actually bundle a bunch of external libraries as part of the software code base. So if you look at things like Embed TLS or OpenThread or OpenAMP, TinyCrypt. So these are all projects that are external projects, but Zephyr effectively takes snapshots of these projects and hosts them in their tree, so that you get a very well-rounded tested configuration when you want to build a Zephyr product. Embedded Linux, on the other hand, is slightly different. So build root with embedded Linux is similar to the way Zephyr does things, in the sense they also package these external packages as part of the repo, as part of recipes. But it's a newer and smaller project. When the de facto standard, because it's a much older project and because it's a Swiss Army knife of very powerful tools to do embedded Linux development, is Yocto. And this is what Yocto looks like to a newcomer. So it's, as I said, a Swiss Army knife, very powerful set of tools, very well done. It's very easy, if you know what you're doing, to make your own distro to support your products. It supports, I don't know, 9,000-10,000 external packages. There's a lot of layers. But outside the core packages that are maintained directly by the Yocto project, the quality varies quite a lot. So you would find multiple recipes to package up the same piece of library that you're interested in, because that's the way somebody decided to package it for their specific use case or their specific recipe. So when you go with Yocto, your choices are clear cut here. That you need to do your homework. So this is what you end up with. This is what you end up with when you go to IKEA, right? So you end up with a set of recipes, a set of instructions. You basically need to comb through all those layers and those recipes to figure out the parts you need, the parts that you want to drop, and maybe override with different policies of your own. And that actually led to the idea for this presentation and for the project that we are currently working on. So what if we could pick up the best of both worlds, from the Zephyr side of how they do things and from the Yocto Linux side, to allow building an operating system that makes it very easy to develop products on. So instead of just Yocto being allowing you to make your own distro, can we do something better than that? So at this point, I'm going to maybe take a pause and ask if there are any questions. Okay. So what I am talking about in terms of this new operating system is basically an operating system for all kinds of scenarios, right from tiny microcontrollers to CPUs, right from tiny sensor devices all the way to more powerful industrial or even mobile phones for that matter. Christian, I have lost speaker access again.
You had?
Yes.
I didn't do anything that is
Well,
surprising.
my presentation shows up for download now, but yeah, okay, I'm at that.
Okay, James briefly was presenter for whatever reason, so I think you should have given you control back, James.
Sorry, what was that again? Was it a question?
Does it work for you now? James briefly made himself presenter apparently. Okay, it works now.
Yeah, it does. Okay, so so effectively, this all scenarios operating system is, I mean, very crudely put, it would be a policy configuration layer on top of existing Linux and Zephyr upstreams. So let's see how we would build this up. Let's take a minute to understand that. What you would end up with is, okay, you start with your Linux kernel, you start with your Zephyr SDK, and you then wrap it inside Yocto, because Yocto allows you to do these kinds of things very easily. For example, Linux has been supported out of Yocto for a very long time, so that's not the issue. Zephyr, there's a meta Zephyr layer in Yocto that can be used to compile Zephyr using the CMake build system of Zephyr. So you can do that. Zephyr does have another build system called West, and I'll come back to that later. We have some ideas on whether we want to improve this Yocto layer in some ways. On top of this, inside your Yocto wrapper, first thing I would do is have a tool chain. So I would have a common set of tool chains which would work across the two projects. So I would consolidate the version of the tool chain. I would consolidate whether it's going to be GCC or LLVM. What would be my configuration flags, hardening features, and so on and so forth. So I would use something that's compatible and maintainable across both projects. Then I would add a common set of security policies. So here, things like secure boot. So are we using common versions of the OptiE, TFM libraries? How do we perform CV checks, and what's our support policy like? What are the key provisioning tools? So when I have a product and I want to make 1 million of them, and I want to provision them with keys, what's the infrastructure like to do that across the two ecosystems? So that's what I would think about in the security policy. On top of that, I would start thinking about OTA by default. So instead of having this plethora of options, I would want to figure out, okay, let's see what I can get common across this. So let's see what my flash partition layouts are going to look like, and what is the OS specific software that I need to work with on the Zephyr side as well as the Linux side for OTA to work seamlessly. So on the Zephyr, for example, you have the DFU and the MCU manager, which run on top of MCU boot, right? And on Linux, you have Rauk, you have OS3, you have a variety of things. I would pick one and effectively make the rest of the tooling work with this on the Linux side as well as the Zephyr side. On top of that, there is networking protocols, which again is a very wide gamut. So we are talking all the way from application protocol libraries, so things like CoAP, MQTT, WebSockets. So again, have common versions of these libraries across the projects. Radio technologies, so there's OpenThread, BLE, Wi-Fi. You can have common versions of, let's say, the OpenThread libraries and use common configuration parameters, for example. We've done a bunch of work in this area for getting bootstrapped And we've run into interesting problems when we try to make our Zephyr devices talk to our Linux devices, all being built out of the common software infrastructure. So, for example, we found some tricky bug in the Bluetooth 6LoWPAN code, which handles the direct peer-to-peer communication. On this side, the client was Zephyr, and we found interesting errors, and it led to a patch that went up, that was posted upstream and still needs some follow-up. On the Zephyr side, we struggled a bit, at least on the low memory devices, with the heap size, for example, because the protocol stack crashes with very hard to debug protocol errors, and you don't know what the error is and whatnot. So we found finding the right balance of the memory size, the heap size that is dedicated to embed TLS on Zephyr. That was an interesting exercise, and there might be some ideas around how we can make it simpler. Once you have all of this scaffolding in place, you then end up with your application framework and a UI framework, which would allow somebody to write applications and generate some basic user interfaces. For a lot of embedded Linux use cases, it is not, they don't need to be 3D accelerated or have to be very fancy UI features like on mobile phones. So something simpler like LVGL, which is already supported by Zephyr, could be used. Or we could go with Qt if the licensing is right. It's something we need to check at this moment. There would be an agent framework, which effectively allows devices to talk to each other, discover each other's capabilities, and offer some sort of context-aware reconfiguration. So what I mean by context-aware reconfiguration is if I am on a video call on my phone and I walk into my office where I have a nice big screen with a webcam, then this agent framework could, in theory, be able to transfer the call from my mobile phone to my desktop without any interruptions. So this is coming down the pipe. We're not there yet on the agent side of things. Sensor framework, obviously, Linux, Zephyr both have subsystems which will allow sensors to read data. Now that needs to be made available to applications. So you would need something of that sort. I did notice that on the Zephyr, in the Zephyr GitHub, that the Android's context-aware, what is it called? Context Hub framework is being considered for inclusion as an external module. So that would be an interesting one for the sensor framework. But once you have built this, do we stop there, and why? So we've already built something with a lot of opinionated defaults. So instead of being a normal Yocto layer where I just do something for myself, I'm saying that, okay, this is a set of recipes that somebody can take and get all of this stuff that I've outlined out of the box if you build products using this stack. So these opinionated defaults are things like, okay, what's my libc version? I mean, is it muscle or is it glibc? What are the kernel configuration options that I will turn on for every device built using this framework? Toolchain flags. What kind of hardening flags am I going to do this? So yeah, the question. So MetaZephyr was created before West was a thing. Patches welcome. Absolutely. So we've already contributed to MetaZephyr. If you are the maintainer, hi. Thanks for taking our patches. And we have some ideas around maybe extending MetaZephyr at some point and seeing if we can maybe move it over from the CMake system to to maybe using West as a thing. So stay tuned. We will get in touch at some point. So yeah, why stop at just the building blocks? So the next step we would like to take is actually blueprints. So what I call blueprints are effectively minimum viable products that go beyond what, let's say, a Zephyr sample application does. So Zephyr sample application would tell you, okay, connect this sensor to this board in such a way, or I2C, run this program, and yes, you can read the data. Yes, great. But that's all it exercises. We would like to go beyond that. So if we are building this framework and we are able to build Linux-based products and Zephyr-based products, I would like them to talk to each other. So why not create like a door lock blueprint, which is effectively the minimum viable product for a door lock. And not only does it the basic features of a door lock, but it also offers features like, okay, if this is going to be accessed over Bluetooth. I mean, all the smart door lock features that are currently available in the market, but some of them are just terribly implemented. So instead, we show them the way on what the best practice would be for out-of-box support for things like OTA, things like how network communication should be encrypted and whatnot between a Linux-based IoT gateway and a Zephyr-based door lock, for example, or smart light. So that's the idea, that we take this a step further. And if you do this right on community hardware, for example, a Raspberry Pi 4 or an Arduino BLE Nano that runs Zephyr, it's very cheap then at the $20, $30 price point for anybody to be able to reproduce this, contribute back, and keep improving these products. What we found is that by doing this, it actually forces us to look at all the corner cases of delivering a product into the hands of customers. And it will also attract OEMs as a result. If they can go a step further, then here's a bunch of Lego bricks and now go figure it out. So that's the idea behind taking it to the blueprints. Any questions? I'm going to take a second here. Right, so Karim, yes, I did talk about build root initially. I agree. So this would be very interesting indeed, because to me, build root is actually quite similar to how Zephyr does things in a lot of ways. It is still a new project, and Yocto just does things that build root doesn't or doesn't want to support, because they're trying to keep it simple. So I do use build root for my personal projects, for example, because it's simple enough. But a lot of customers do want the fancier features of Yocto. So I agree that at some point it would be very interesting to engage with the build root community and seeing if they would also be interested in this. And I will get back to this again with my next slide, because it actually comes back to the point you're making. I've talked about, okay, there's a vision, I have a dream, but what is the low-hanging fruit? What could we do to kickstart an effort around this? We've already done some work around this, but I think we are now ready to go live in a few weeks to engage with the rest of the communities. So what are the kinds of proposed improvements I would do? So one simple one would be library versioning. So if there is a version of a library, let's say embed TLS or OpenThread, that is hosted in the Zephyr code base, And then there are Yocto recipes, and as Karim said, build root recipes. If we could agree as upstreams, so every upstream will have to make their own decision about this. But this is something I would like to at least attempt to do. To sync across these versions, it saves a lot of engineering effort. So IP compliance is the simple one. So you just have one package for a library that you need to do IP compliance work against. But it's also your entire security team, which is backporting bug fixes and finding bugs in versions of libraries. So if you actually try to do that, you end up with benefiting all projects involved by syncing library versions. If upstreams are not open to this idea at this point, I'm guessing at some point we would have to start carrying them patches to up level or down level library versions, so we can have this common interface in the layer I'm talking about. But the attempt would be to actually engage with upstreams about it. The next one would be as someone else pointed out, extending the meta Zephyr class to use the West build system. It makes sense because West offers a bunch of functionality that is not present in the CMake version, and it just makes things easier for both the Zephyr community as well as so you would effectively end up with something like a big bake class which understands West commands and deals with it. How about improving device longevity? So this is an interesting one. So I looked at Zephyr, I looked at Yocto and read-only file systems. You would assume that's a thing that easily, something that you can easily toggle on. And yes, it's true. Same thing on build root, I believe. But there are always caveats to read-only file systems. So you have to figure out, okay, what's going to happen on my first boot when I'm generating a host key. So my SSH daemon is generating a host key, drop bear, for example, and it writes it to etc/etc. So what's going to happen then? So you probably want like a read-write, a persistent read-write storage for that parts. And that's not solved. So you can have a read-only file system, but then there's lots of caveats around it. So we actually went ahead and extended that functionality, at least in Yocto, to add support for persistent read-write storage through systemd units. So what you end up with is as part of your recipes, as part of the core recipes in this layer, you define the points where you would like read-write access to the file system, and then you generate systemd units which effectively mount a read-write partition onto those bind mount onto those locations, and it all happens transparently. So we feel it's a nicer way to deal with this problem in a more generic way. Secure defaults. This is again a whole gamut of things, right from the mundane. So the mundane ones are things like what are my key lengths going to be for my SSH keys or for my certificates and whatnot. To something more involved, like do we follow all of the kernel self-protection project, the KSPP project recommendations around what kernel configurations and whatnot. How do I get out-of-box secure network communications? So you can use CoAP or MQTT for your applications, but by default, they're talking plain text. So how do I make it so that it's extremely hard to actually build insecure apps? So security is built into these images. So you would effectively use some version of an SSL library like GNU TLS or Embed TLS, whatever you make your opinionated choice on, and use that out of the box. And then there's the feeling is that if we did a bunch of these things, it would actually improve developer experience quite a bit. Because now all of this is pre-configured out of the box for someone to build a device around, and they can focus on their application rather than all of this other extremely important core functionality, but which requires a lot of expertise to get right. But if you do it for them and make it easy for them to use it, I think there will be adopters. One other low-hanging fruit that we have is the SBOM and the license dashboard. So we've done a bunch of work with Fossology, with scan code, to see what our bill of materials looks like. Here's a sneak peek at the dashboard. So this is effectively our CI system when it's building an image and generates the reports from the IP scan, and then somehow converts that into this dashboard that you can come back and look at later and go through different images and figure things out in slightly more easier to parse manner. This is heavily work in progress, so you will hear things about this in the future. But yeah, this is happening. It's happening in a lot of different places, and so it would be interesting to see if we can reuse some of these bits. Finally, and most importantly, I would say, all of this work should happen upstream. So we don't have any grand plans to make this layer like one big fat layer with a lot of policy and patches and whatnot. We would prefer to work with the upstreams in this case, which is Linux, Zephyr, Yocto, Buildroot, to get them around to where this might make sense for them to adopt it. If they do not wish to adopt for some reasons, then we might end up with not just the policy configuration in that layer, but maybe carry some patches for a while we work upstream to get them on board. So that I believe is the most important thing that we want to keep in mind. So I'm basically done here. So in summary, what I'm inviting us to think about is think about Linux and Zephyr as part of a single OS platform for products. So don't think about it just as the Linux kernel or just as Zephyr, but a single platform. And by syncing package versions to simplify your security support, your IP compliance support, and then using a BitBake, a Yocto layer to enforce policy for the platform. So the opinionated set of defaults that I spoke about, you could sort of build devices, build better smart devices that have these features out of the box. And then I'm proposing that we use blueprints to create more realistic products. So more like MVPs, but create more realistic products, not just stop at a simple example, because it does, in our experience at least, it does expose a lot of issues with intercommunication, standards between Linux and Zephyr, and memory constraints on MCUs and all of that stuff. So we definitely want to work upstream for all of this. And in my view, if you use the broader Linux plus Zephyr ecosystem use cases, so a door lock running Zephyr talking to a IoT gateway running Linux, that sort of use case is what I have in mind. Then you can drive standards around security, networking, OTA for the future of these kinds of IoT devices. That's the goal, at least. to make better products around this. So there's a comment here on chat. Yocto can generate NSBOM as part of your build. Yes, we are following that work. It's recent work as far as I understand, and it is interesting. So yes, we will reconcile the work we've done to what is happening inside Yocto and see what we can contribute back, what makes sense there. Another comment is Yocto can also do reproducible builds, which is something of interest for security. Absolutely. So we are already using that to be able to reproduce builds. So once you tag a release of this all scenarios operating system, we would like to be able to reproducibly rebuild a Zephyr as well as Linux targets for that. So the manifest effectively controls what is the version of Zephyr and Linux that we are going to pull in. At this point, we are on 5.10 LTS for Linux and the 2.6 LTS for Zephyr. So that's what we want to pull in.
Cool.
And then how am I doing for time?
You're done.
Oh, okay. So, well, good. So stay
Perfectly
tuned.
on time.
So stay tuned for more announcements at ELC that's happening. And thanks for listening.
To be clear, we have 15 minutes gap, so don't feel chased off the stage. The next one doesn't start 15 minutes.
If there are any other questions, I'm happy to answer them if you want to stick around.
Yes, so we're going to have a 15-minute break. And then we will be back with our next talk by Yasunori and Ruan about the forefront of the development for NVDIMM on the Linux kernel. So see you back in about 15 minutes.
Yeah, so if anybody is interested, Stefan Schmidt is talking about the IoT Gateway Blueprint in the IoT microconf tomorrow. So you might look at that, and you'll find more talks at ELC around this. Hopefully, we are ready to make reveal more details by then. Thanks a lot for your time.
So, hello. We're about to start the next talk soon in a few seconds. So I hope everyone is back by now. And let me just switch on the slides real quick. I'll hand it over to you in a second. Okay. Yasunori, I made you a presenter now.
Yeah, I'm here. And Ren-san, could you confirm you can also control this presentation? Or only one person? Oh, okay, I can control it.
You can control it, right?
Yeah, okay. Ren-san, how is this? No?
I think I need to make him presenter. I think only one person can be presenter at a time. But what you can do when you want to hand it over to one, you can just click on his name and I guess make him presenter. And if not, I can do it during the presentation.
Mm-hmm.
Is that okay?
Okay. First off, I'll talk my part, and second part, Ren-san will talk. So I'll give
Okay, you just give me a heads up.
my authority.
Okay, cool. So then welcome to the second session during this referee track talk. Great that you're all here. The next talk is going to be by Yasunori and Wen about the forefront of the development for NVDIMM on the Linux kernel. So thank you.
Okay, thank you very much. My name is Yasunori Goto from Fujitsu. Today, I'd like to talk about the forefront of the development for NVDIMM on Linux. Here is the agenda. At first, I'd like to talk about summary of current status of development for NVDIMM, its basis of NVDIMM on Linux, and issues of file system DAX. DAX means direct access mode. And next, Ren-san will talk about a deep dive to solve the issues of file system DAX, its support reflink and DDIV for FS Dax, and fix NVDIMM-based reverse mapping. Then we will make conclusion. Let me introduce myself. I have worked for Linux and related OS since 2002. And I developed for memory for trouble feature of Linux kernel and work for technical support for troubles of Linux kernel and etc. And currently, I am leader of Fujitsu Linux kernel development team. So in the last few years, I have mainly worked for NVDIMM. For example, I worked for some enhancement for RAS of NVDIMM, like fault location or fault prediction feature. Okay, let's start the basis of NVDIMM on Linux. So, at first, I'd like to talk about the characteristics of non-volatile DIMM. It's persistent memory device which can be inserted to DIMM slot like DRAM. So CPU can read and write NVDIMM directly, but it can keep data persistency even if system is powered down or rebooted. So latency, capacity, and cost have characteristics between DRAM and NVMe. So use case is, for example, in-memory database, hierarchical storage, and distributed storage, and KVR store, and etc. And famous product is Intel Data Center Persistent Memory Module, as you know. So impact of NVDIMM is very huge because traditional I/O layer becomes redundant for NVDIMM. At first, page cache is redundant because it was created for slow I/O storage, but NVDIMM is fast enough without page cache. Next is sync system call or fsync or msync system call. If user process calls CPU flash instruction, then it's enough to make persistency. The third is system call. It means switch to kernel mode. application can read or write to NVDIMM directory, as I said. Even system call may be a waste of time due to switching between kernel mode and user mode. So new interface is expected for NVDIMM. However, NVDIMM is difficult for traditional software. Many software assume that memory is volatile yet. So what will be necessary for software to use NVDIMM? At first, it's needed to prepare for sudden power down. Especially in older CPU, its cache is still volatile. If system power down suddenly, then some data may not be stored. Next is it needs data structure compatibility on NVDIMM. It should not change data structure in NVDIMM. If the structures are changed, software update will be cause of disaster. The third is it needs to detect and correct crossbeam data. If the data is broken, software needs to detect it and correct it. And finally, software needs data area management. Software needs to assign not only free area, but also user area for reuse its data, even if it's rebooted. In addition, kernel must assign the area to suitable process with authority check. So there is a confliction of requirements. At first is file system is still useful. File system gives many solutions for the previous consideration. Format compatibility of file system, data collection, journaling or copy on write, region management, authority check, and etc. So it's useful for current software. But file system is too slow, as I said. Traditional I/O stack is too heavy. So CPU cache flash is enough to make persistency. So it need a new access interface to NVDIMM for next generation software. Because of previous reasons, Linux provides some interface for applications. First is green line, storage access. Application can access NVDIMM with traditional I/O interface like SSD or HDD on this mode. So application can use this mode without any modification. Next is file system Dax. Page cache is skipped when you use read or write on file system Dax, and application can access NVDIMM area directly if it calls mmap for a file. But it needs file system support like XFS or ext4. And this mode is suitable for modifying a current application for NVDIMM. The third mode is device Dax. Application can access NVDIMM area directly if it calls mmap for /dev/dax device. This device allows only open, mmap, and close. In other words, you cannot use read or write nor any other system call. So it's for innovative new application with NVDIMM. In addition, PMDK is provided. It's a set of convenient libraries and tools for file system Dax and device Dax. Well, some libraries support transaction for PMM applications, and some tools provide tools management in the Dax file or devices, and etc. So NVDIMM is shown as a device file like storage when you created a namespace. For storage access, /dev/pmm and number and s is created. For file system Dax, /dev/pmm is created. And device Dax, /dev/dax is created. ND controller can create this device when it's created namespace. Here is an example of file system Dax operating. In addition, you can make file system on /dev/pmms or /dev/pmm. Please note one point. Device Dax is character device. So since you cannot use read or write for device DAX, you cannot use dd command for backup. So you need to DAX style command of PMDK instead of it. Unfortunately, file system DAX is still experimental status. I believe file system DAX is a very expected interface. The management way of NVDIMM is almost same with the traditional file system. So operator can use traditional command to manage NVDIMM area. Not only application can access NVDIMM area directly, but also it can use traditional system call. In contrast, device DAX requires pool management by tools of PMDK. Otherwise, our software needs to possess whole of the namespace. In addition, application cannot use many system calls in device DAX. However, file system DAX is still experimental. Its message is shown when the file system is mounted with DAX option. There are difficult issues in kernel area for some years. So I'll talk what is the reason. So issues of file system DAX, what is solved and what is current state, current issues. So, in summary, there are two big reasons. The first is file system DAX combines storage and memory characteristics. This causes corner case issues of file system DAX. They are often difficult problem. Second is more additional features were required, but they were difficult to make. First feature is configuration DAX on and off for each inode. And next is coexistence with copy and write file system. First corner case issue is update metadata problem. In file system DAX, we expected that application can make persistency of data with only CPU cache flash, as I said. However, this also means that there's no chance to update metadata by kernel or file system. So, update time of the file may not be correct. In addition, if application use or write some data to file on the file system DAX, and a user remove some blocks of the file by truncate system call, kernel cannot negotiate it. So data of the file may be lost. So if data transferred by DMA or RDMA to the page, which is allocated as a file system DAX, similar problem may occur. So current status of update metadata problems. For general write access like normal application, it was solved by introducing a new map sync flag of mmap. When this flag is specified, page fault occurs every write access. Then kernel can update metadata this time. PMDK specifies this flag already. For DMA or RDMA data access, it occurs in kernel or driver layer. It's solved by waiting truncate until finishing RDMA or DMA. But there is some card like InfiniBand or video card. Its DMA or RDMA is occur in user process layer. In this case, it's not solved. Truncate cannot wait completion of transfer because it's made too long time. Fortunately, there's a workaround. It's on-demand paging. In ODP, usually a driver or hardware does not map the pages of DMA or RDMA area for application. And it maps the page when application accesses them. So kernel or driver can coordinate metadata at the time. Mellanox, now NVIDIA newer card has such feature. Next is a new problem. It's unbind problem. Unbind is a CCFS interface to disconnect or hot remove a device. Each device driver provides its handlers for it. Though NVDIMM is not hot plug device physically, its interface can be used to disable and switch the mode of NVDIMM namespace. For example, to change namespace mode from file system Dax to device Dax, next is to allow that user can NVDIMM like normal RAM. This is example how to use device Dax namespace like normal RAM. This uses unbind CCFS interface like this. But unbind is likely a surprising remove interface. There's no way to fail of unbind even if a user is using it. So it must be disabled forcibly. So a race condition was reported between file system Dax and unbind in 21st February. To solve this problem, file system Dax needed to disable a range of NVDIMM area immediately. Currently, this is not solved yet. It will be solved after the end of Ransom's work, which will be talked by him today. His new code will help to solve it. Next issue is Dax on and off for each inode. Its expected use case is the following. The first is need more fine-grained settings. Users may want to change the Dax mode depending on each file. And change Dax attribute by application is the next use case. Configuration is always painful for administrator. So if application can detect and change it, it will be helpful for them. The third use case is performance tuning. Since the write latency of NVDIMM is a bit slower than RAM, user may want to use page cache by Dax offsetting. Finally, final use case is workaround when file system Dax has a bug. What was the problem of this issues? So if file system change Dax attribute, file system needs to change the method of file system between Dax and normal file, but they may be executed yet. In addition, data of the page cache must be moved silently when the Dax attribute becomes off. And these problems were very difficult. Fortunately, this issue was solved. The Dax attribute is changed only when its inode cache is not loaded on memory. File system can load suitable methods for each attribute when it reloads inode to memory. Page caches of the file are also dropped. Users can use this feature with the new mount option, mount-dax equal inode. And Dax attribute is changed by command. Here is the XFS example. Please note one point. All of applications which use the target file must close it to change the Dax attribute. File system will postpone changing the Dax attribute until dropping inode cache and page cache of the file. Next issue is coexisting with copy on write file system. The copy on the write file feature of file system is here. If there is the same data block on different files, file system can merge it as the same block, like this picture. So far, if only file system manages such block, it was enough. Since page cache is allocated for each file of the blocks, memory management layer don't need to know it. But in file system Dax, it becomes problems. merged block equals merged memory itself, so it affects the memory failure case. There are two problems to solve these issues. The first is it needs actual copy and write implementation for file system DAS. Currently, there is no implementation of reflink and delete for file system DAS. IO map, which is a new IO block layer instead of buffer head, has interface for copy and write file system already. And XFS file system DAS also use IO map. But there's no code to use copy and write and DAX at the same time. Next issue is very difficult. It needs to check plural files from a merged page or merged block. When a memory failure occurs, it needs to kill processes which use the memory. To achieve it, kernel needs to find all processes from the merged page or merged block. But the merged page has only one struct page. There is no space in the struct page for plural files in it. So Larson will talk how to solve them. Okay, Larson talk from here. Please give him the authority of the slide controller.
Yes, on my way. Can you quickly, so you should be presenter now. And can you turn on your microphone? We can't hear you right now. Now we can hear you. Oh,
I can hear you. It's okay. It looks okay.
really? Can James?
Go ahead.
Okay. I don't hear anything. Sorry. And James doesn't hear either.
Please go ahead.
Can you, so in the bottom, you see this little microphone, right? There are like three controls: a microphone, a telephone, and like a little camera sign at the bottom of the screen. And the little you click on the little microphone, and this should let you join audio. If not, you can.
Control you.
If not, you can also try leaving the track and then rejoining. Yes.
Hello?
We can hear you.
Okay, thanks. Okay, let me begin. Hi, everyone. I'm going to show you how we deep dive to solve the issues of file system DAX. I will do it in two parts. The first one is how to support reflink/dedupe for FS Dax. And the second one is how to improve the NVDIMM-based reverse. My name is Ran Xiang. I'm a software engineer of Fujitsu Nanda. I used to work in the embedded development, and currently I'm focusing on the Linux file system persistent memory. Here is the background of the issue we need to solve out. FS is still in experimental status on XFS file system. It is because that reflink and FS Dax cannot work together. We can try to use them together and see what will happen. Firstly, create a new XFS file system with reflink feature enabled. and then try to mount it with Dax option. Then we will see the error message. And more detailed reason is shown in the D message. Dax and on XFS is experimental. They cannot be used together. So what are the FS Dax and the reflink, and why they cannot work together? I will explain them in the next pages. The first one, what is reflink? It is a file system feature that files can share their extents for same data blocks. The figure in the right shows the comparison between normal copy and reflink copy. The above part is the normal copy. It costs time and storage space to duplicate data extent. The below part is reflink copy. It won't actually duplicate any data extent. Instead, it just remaps the original data extent to new file. So without data duplication, reflink has these two advantages: fast copy and safe storage. Since these two files are sharing data extents, to prevent both from being modified, we need a copy on write mechanism here. It copies shared extent to new destination before user data is written. So this is reflink. And then what is FS Dax, also called file system Dax? It is the mode of NVDIMM namespace. In this mode, page cache will be removed from the IO path. It allows mmap to establish direct mappings to persistent memory media. So why on earth reflink and FS Dax cannot work together? We have investigated this problem in depth and found two main issues. The first one is we need to support copy on write the dedupe mechanism in FS Dax. The LMAP interface needs to be extended to support copy on write. The implementation of copy on write and dedupe should be added in FS Dax. Another one is we need to improve the current NVDIMM-based reverse mapping by supporting 1-to-n reverse mapping for NVDIMM. So let's start from the first issue: support reflink/dedupe for FS Dax. Firstly, I'd like to compare what's the difference between the normal buffered I/O with FS Dax. Here is a simplified write process of buffered I/O. The main purpose is to describe what it does in IOMAP framework. Initiate a write from user space and then come to IOMAP framework. We will get the destination from IOMAP begin in XFS. In buffered I/O case, it allocates delay extents. Then in actor, destination data is read from disk to page cache. User data is written from user space to page cache. Then mark the page cache dirty. In the last, there is some cleanup work to do in the IOMAP end in case of error. The dirty page cache will be synced to disk later. The sync job contains remapping new allocated extents. As is shown in the figure, the process of using page cache indicates a copy on write mechanism. But this is quite different in FS Dax, even though it uses IOMAP framework as well. In FS Dax case, it allocates immediate extents in IOMAP begin. The actor also does quite different things. Get NVDIMM address by calling direct access and write user data directly to NVDIMM without any page cache involved. What's more, there is no extra work in IOMAP end. Since there is no longer a need for sync, there is no opportunity to remap new extents. By comparing with the previous buffered I/O, we can see that the copy on write mechanism is missing in FS Dax. So to solve this issue, what must be implemented? Looking to the IOMAP framework, we need to allocate new extent for copy on write use and store source extent info somewhere. So we introduce a src map to store the source extent. Then we copy the source extent data to new extent and write user data into it. This is copy on write operation, which is needed in write and mmap pass. Remap is also necessary after copy on write. IOMAP N is a good place to do that. In the last, we still have to implement a DAX-specific dedupe method. The first necessary thing is the source extent info. IOMAP framework only uses a structure named IOMAP to tell actor the destination, where and how long the data to be written. But it is not enough for copy on write mechanism. To implement it, the source extent info is also needed, including its start block number, which means where to copy from, the length, which means how long to be copied, and the flag if needed. Now, kernel developer Goldwyn has introduced another structure named src map to remember and pass the source extent info. The next necessary thing is to fill the members of src map. XFS only fill IOMAP at the end of IOMAP begin. We need to let src map to be filled too. As is shown in the flowchart, when it starts to write, we find the destination extent firstly. If it is a shared extent, which means needs copy on write, we allocate new extent. The destination we found should be treated as source extent because all changes will be made in the new allocated extent. So the src map is filled by destination extent. The IOMAP is filled by new allocated extent. And then set the IOMAP F shared flag for actor use. In the DAX actor, adding copy on write mechanism is also necessary. The current actor only writes user data to destination by a DAX-specific interface called direct access. It is used to translate IOMAP to NVDIMM address. So before user data is written, we need a pre-copy. See the flow chart. We see the flow chart. We add a copy on write branch to get source address from src map and copy source data to destination address we get at the beginning. After that, we write user data to destination address. In this way, copy on write is able to be executed in write path. In mmap path, adding copy on write is also necessary. Different from normal page cache fault, FS Dax has its own specific fault handler, page fault handler, which uses IOMAP framework too. But for now, it only finds the destination page and associated VMA. To support copy on write, we need a pre-copy before associating. We use direct access to get destination address, and in addition, the PFN, which is for associating usage. Then, similar with the previous, we get source address from src map and copy source data to destination address. After that, associate VMA with PFN we got at the beginning. So at this point, copy on write mechanism has been added in FS Dax. Since FS Dax is synchronization, we need to remap extent we changed before right now. Otherwise, because the new allocated extent is not mapped, the metadata will not be updated. As a result, the file will not contain the copy on write extent. IOMAP end is a perfect place to do this job. In addition, if something wrong happened in actor, it is also a perfect place to clean up those extents. Besides copy on write mechanism, deduplication is also necessary to be adapted to FS Dax. It is used to reduce redundant data on storage costs. The core function is to compare a range of data byte to byte from two files to check if they are same. There is a general compare function for normal files. by comparing data read in page cache. However, FS Dax has no page cache. So we need a Dax-specific compare function to compare data by accessing data directly from NVDIMM. As is shown in flowchart, direct access these two files to get their NVDIMM address, compare data on it by calling memory compare to get the result, same or not. If same, it means the range of two files can be deduced to share same extents. Till now, we are able to make reflink and FS Dax work together in write and map paths. However, it just looks functionable on the surface. In depth, there is another issue to be fixed. As a block device, NVDIMM permits files on it to share same data extent thanks to reflink. Since it is NVDIMM, we have to think it as a memory device. In other words, files are sharing the same memory pages. So the memory management layer needs to understand the shared block. In the next pages, I will show you how we solve it. As a memory device, memory pages may fail in hardware level. That means the page could not be accessed anymore. The kernel triggers memory failure to handle this failure. When memory failure occurs, the system will track all processes associated with the broken page and then send a signal to kill those processes. The track from memory page to a file is usually called reverse mapping. In this case, we call it NVDIMM-based reverse mapping. The current NVDIMM-based reverse mapping can only support one page to one file mapping. However, for reflink, because files are sharing same pages, we need to improve it to support one page to multiple files mapping. To achieve it, I have thought of many ways. The first idea is described in the right figure. It was simple to be implemented and worked, but it is not a good idea because of the huge overhead. After that, I have tried solving it in many ways, but any of them was not perfect. The current strategy is to trace file system internal to find the one-to-n relationship, but there are still some difficulties needs to be solved out. Let's see how memory failure signal works through the associated layers in kernel first. In the middle of the figure, we can see two processes are sharing one DAX file. Then MC triggered because of the shared page inside the file was broken. Memory failure takes over this exception and initiates a reverse mapping from the top to the bottom. From MM layer, device driver, block device, file system, files, and finally to all processes using the broken page. Finally, send signals to process to kill them by signal bus. So an enhanced reverse mapping is the key to solve the problem. Since it spans many layers, we need to implement the reverse mapping on each layer. The first one is from NVDIMM driver to DAX device. The second one is from DAX device to file system. This is the most complicated one. We need to introduce DAX holder registration mechanism to deal with different ways of using a storage device. The third one is from file system to files, which requires RMAP B-tree feature. The last but not least thing is the compatibility for no reflink and the no RMAP B-tree file systems. For example, ext4 file system. So we will start from the first issue. The memory failure now accepts PFN as its argument. It is the page frame number of the system memory. We need to translate it into the offset in NVDIMM firstly. And then, according to the mode in use, the offset needs a further translation by each driver. For FS Dax mode, PMEM driver translates the offset linearly. For device DAX mode, the DAX driver needs to calculate offset according to the DAX range property inside. In this session, we only take FS Dax mode into consideration. So for now, we have got the offset inside the PMEM. PMEM is also a block device, so it can be used in many ways as other block devices, such as making file system directly, putting in many partitions, creating LVM to combine many PMEM devices, or even creating nested partition and mapped devices. So to make it suitable for each kind of usage, we introduce a DAX holder registration mechanism to abstract them into one behavior. So the holder represents the inner layer of a PMEM. It is registered when the holder is mounted or initialized. The one behavior for each kind of usage is notifying failure into inner layers. They need to implement a notify failure interface. Let's start from the easiest one. The inner layer is file system. This case is created by makeFS directly on a PMEM. There is no partition inside the PMEM. The reversed mapping translation only needs to remove the fixed block device header length. The second case is that inner layer is a partition. This is created by partition tools. It could be one or more partitions inside the PMEM. We need to find which partition the broken page locates in so that we can get the offset in inner layer. The translation is to remove the start offset of the partition we have located. The mapped device case is a bit complex. It is created by LVM toolset or other tools. It creates many DIMM targets. The DIMM targets can be used in many ways as well, such as linear target, RAID, crypt, and so on. So before introduce translation method, we need to introduce reverse mapping for each kind of DIMM target first. This reverse mapping is the reverse process of the exist map interface of DIMM target. With its help, the reverse mapping for mapped device is able to achieve. We iterate all DIMM targets in the mapped device to find out which targets contain the broken page, and then remove its start offset. After the translation, we need to handle layers inside the mapped device. This is the interesting thing. The inner layer could also be file system or even partition. So thanks to the holder registration mechanism, the inner layer could also be treated as holder, so that the reversed mapping for mapped device is able to go on. Finally, it comes to file system. Reverse mapping from file system to files requires unmapped feature, which is by giving an offset and length, we are able to search for extents contains it. Fortunately, XFS provides the Query API. The search result could be file content or file system metadata. For the former case, we need to send a signal to kill processes using this file and trying to recover file data. For the later case, it is hard to recover a file system online. Just shut down file system and report error. Now that it is possible to find all files by the 1 to n reverse mapping, and the original page-based process collection and the kill function should be modified to file-based. As we know, ext4 doesn't support either reflink or unmapped feature. So we need to keep the compatibility for file systems like this. Firstly, keep the original one page to one file reverse mapping. This relationship is created by associating pages mapping and offset to a files mapping and offset. It should be only associated once, otherwise error is reported. But to make it compatible with 1 to n reverse mapping, we make some restrictions to avoid the error. Just make it associate only once and only for first time. Secondly, keep the original reverse mapping routine. With the support of first compatibility, the original page-based reverse mapping still works. So keep it and fall back to it when we get operational support error in the 1-to-n routine. So the 1-to-n reverse mapping has been implemented so far. It can be compatible for all NVDIMM modes, compatible for all usage of PMEM, compatible for all file systems, with more driver or file system support in the future. Now we have some future work to do, such as fixing the race condition against the unbind. With the help of the 1-to-n reverse mapping, I think this can be fixed. We hope my code can help this case. Then let me make a simple conclusion of today's session. We have talked about the basics of NVDIMM for Linux and the issues of file system DAX and how we deep dive to solve the issues of file system DAX. Okay, thank you for listening. Thank you very much.
Thank you. This was perfectly on time. We do have a 15-minute break coming up, and we can no problem. I looked at your slide, so we can no problem answer questions and go a little bit into the break. This is not a problem, but if no one has any questions, we will resume in 15 minutes.
Okay.
And I do encourage people really to turn on the camera and ask their questions. Hey, Derek.
Oh, hi, Derek.
Hello. So I have, well,
Okay.
since we haven't actually had any other DAX sessions at LSF this year, I was kind of wondering, or I was particularly curious about to hear from you and Dan. Oh, look, there's Dan. About
Hi, Dan.
what's Christoph going on about let's completely divorce PMEM from the block layer and rip out all that stuff and then apparently re-implement LVM type things on top of PMEM.
Oh,
If anyone else would like to ask a shorter and less loaded question, they're perfectly welcome to go ahead of me, but I was kind of wondering, like, does everybody, is that the plan of record for PMEM going ahead? Like, completely disassociate it from the block layer and all of it's gone, and like, I guess we'll just have to rewrite all of XFS too, or what?
You want to jump in here, Xiang, or I can try to take that one. Like, if you look at some of the problems that the device mapper caused, like every time we do anything interesting in DAX, we have to go plumb like every single device mapper target with new functionality. The other thing that like this stuff is just memory, so like remapping it and concatenating it and doing that is pretty trivial. So like a lot of the complexity the device mapper has for block devices and splicing bios and all that kind of stuff is just not important for this stuff. We also have the case that like that people are wanting to chop these things up and make them discontiguous, and discontinuity is not something that block devices have ever kind of done. They've had partitions that are contiguous, but DAX devices don't really need that. And it's actually been pretty flexible to do that. And then lastly, like the new CXL stuff is going to allow you to combine devices and interleave devices and basically do a lot of RAID kind of type things at the hardware level. And so at that point, the hardware is replacing device mapper, there's cleaner ways to do it, and we don't have to keep plumbing every time we want to do anything interesting in Dax. We don't have to keep plumbing everything all the way through 5 or 6 block drivers. So I'm worried about all the things that are going to break when we lose block devices, but at the same time, like it's cleaner going forward that we don't have this kind of legacy.
All right, yeah, because some of the things that have gone on the list this week have set off a tidal wave of, wait, you guys are going to completely mess the whole thing up again? We just barely got it working with, it's our large well-known software project.
I just got this bucket of bolts back together. Oh my God, something tearing apart again. No, but like I think Christoph's plan was like, hey, we'll deprecate it and then we'll delete it in a couple of years. I don't think it's going to be deleted. I mean, I think we'll add support for DAX mounting, and block compatibility will still be there, and that'll never go away. So I think we'll have a legacy block path that'll be there forever. But it just won't get new features like this, the shiny reflink stuff, which is would only be for the new way. At least that's what I'm thinking. Like there's too many people that are mounting on Dev PMM 0 that we're not going to change. They've been doing that for 5 years. We can't get rid of that.
Okay, and the other giant question I have was about the other thing that Christoph was complaining about how the memory manager still kind of doesn't know how to deal with this page thinks it's owned by multiple owners. And I mean, I am super afraid to wade into that discussion because look how badly Folios has gone. But I don't know. I mean, I kind of thought that the memory failure patch set was basically an end run around it. If you have these magic hooks to do it yourself, then we'll forget about the memory manager because the FS knows better or something like that. And if you don't have it because ext4 or whatever, then we just assume you don't get sharing or fancy reflink features, which is fine because ext4 doesn't, and we'll just use the old MMRMAP path and be done with it. Or I guess, given the other session earlier in the week about better error handling, we could also just shut down the entire file system and reboot the node immediately.
I mean, yeah, but I think that's what I like about Xiang's patches is like for the first time, like giving the OS a chance, giving the file system a chance to participate in memory failure versus like if you read the memory failure code, it's trying to guess the state of pages and it kind of gets it right most of the time. I think like asking the agent that knows about it is I think is a good change in direction.
Yep. All right. Well, I guess next week, I guess I'll get back to poking around at those patches because I've seen that there's been like 100 odd emails that have flown by on the list, and the only one I've had time to pay attention to is the RWF clear poison or whatever that is morphed into now.
Thanks for the discussion. What I wanted to point out is you want to keep continuing the discussion, you can either move it into a hallway track chat channel, which is not ideal, but it's at least an option. The other option is all of the hack rooms are currently empty as well, so you can also just join a hack room and continue the discussion right there.
Okay.
Just a
okay.
FYI. Thank you for the talk.
Thank you very much.
Okay, thank you very much. Thank you for help asking a question.
Paul, I don't know if you can hear me, but I'll just put up your slides and then I'll hand presenter over to you. So you don't need to do anything. Yes, Paul? You did raise your hand, I think. Hello, Paul. I already made you presenter and put your slides up. We have like 1 minute left, but. Oh, I can't hear you, Paul.
Maybe I should unmute myself.
Yes.
Used to run a presentation in the early 90s that had was computer in general, both hardware and software topics. And if it was a hardware topic, the guy showed up like right at the beginning of the social half hour. If it was a software topic, they mostly showed up in the 5 minutes just at the beginning when the presentation was supposed to start.
Excellent. Okay.
All right.
I think we can start. I don't think I need to give a long introduction who Paul McKinney is, but he was actually also the first person who supervised my first referee track talk at Plumbers. So now I can give it back.
The impressive part is that you survived the experience. Good on you.
Excellent. Not just torturing RCU. I take it. Joking.
Well, you know, sometimes you just have to have a habit forming or something.
Yes. Okay.
Okay.
So,
Thank you.
Paul,
Thank you, Christian.
great.
This is just about torturing RCU, and of course, well, you know, RCU has caused some pain over a while, so it's natural for a lot of people to want to torture it. I do the most torturing of myself, so here I am. But actually, I'd like to call for a round of applause and appreciation for the people that torture software. I've just listed a few of the projects that have found problems in my code that came to mind that fit on the screen. There's a lot more. The thing is, you know, RCU gets the press, but without RCU torture, it would not be what it is today. There's a huge amount of benefit that RCU torture and these other test things provide as well. That really contribute to the robustness of the Linux kernel in general and RCU in particular. Okay. Of course, there might be the opinion that people just, you know, shut up and let me start torturing RCU. It's tortured me enough. I want to get back at it. Okay, you know, here you are. So it doesn't take much, really. If you have a suitable system, you got QEMU and KVM. I use x86. Some people use ARM. There's been some PowerPC. Although I don't run them myself, so I can't speak to how well they work. But set up your path. I don't normally set up the path, but it makes the stuff fit on the slide, so I pretended I did in this case. It's really easy. Once you've done that, kvm.sh, enter. And that's going to do 30 minutes of torturing on each of 19 scenarios of different kconfig and boot argument parameters. That means it's going to run at single threaded, so that means it's going to take about 10 hours. You know, 19 half hours plus kernel build time for 19 kernels. And if you have a large machine, say you got 64 CPUs, the next line might be more appropriate. And what that's going to do is it's going to run as many scenarios as it can concurrently. And in this case, currently, that'll get you done in 2 batches. So an hour plus 19 kernel build times. So a lot faster. On the other hand, if you have to tell it how many CPUs there are in all of your machines all the time, that gets really old. And so the next line shows -- all CPUs, just run as many CPUs as we got. And you can also specify duration. In this case, run them for a day, and you might do that for a weekend run. Or you might have a really big machine. You only want to use part of it for torturing. So maybe you say CPU is 128, 12-hour duration. And trust makes so you don't rebuild things unnecessarily. 128 CPUs is enough to do all the scenarios in one batch. You still do 19 kernel builds, but 1 hour of torturing and get 19 tortures happening concurrently. In some cases, you might, for example, you might be annoyed at SRCU particularly, so you might want to torture just the SRCU aspects, SRCU scenarios. The next line, 16 CPUs, and run 2 each of those scenarios, and that'll get your default of 30 minutes torturing each. Now, one of the things that's going to happen is you might be chasing a bug that happens at boot time sometimes, not often. In that case, the kernel build time starts really getting painful. All right. And so there's something called KVM again. You give it a path, the old results. The output of a previous run would have said results directory and given you a path name. You take that path name, you throw it in as the first argument there, path to old run results. Maybe a duration of 45 seconds. So there's no kernel builds, it just uses the kernel you had previously. And you can run that over and over again very quickly and much more quickly reproduce your boot time hang or panic or whatever it is. One of the really nice things, thanks to my current employer Facebook, is that I can have lots of systems. And so there's something KVM remote that allows you to run a bunch of RCU tortures on a bunch of systems. In this case, we're showing a list of them. sys1, sys2, and sys20 need to be names of systems you can non-interactively SSH to. Okay, fine. You could interactively do it, but you're going to be typing your password or doing whatever you do a lot. So I'd recommend making it so that it can just happen without human interaction. And in this case, if each system has 80 CPUs, the script assumes that all the systems have the same number of CPUs. And then in that case, we're talking 20 times 80, 1600 CPUs. You'll want to do a lot of scenarios, repetition scenarios. In this case, dash config says tree 10, which isn't normally run. It's a fairly large scenario, 56 CPUs, remember correctly, that's non-preemptive. And then we're saying 15 times CF list says run everything you normally run 15 times. CF list is kind of a placeholder for all the 19 that it does. Okay, so there's your instant gratification. You can just go right now and torture CPU, torture RCU, excuse me, fairly thoroughly in different ways, given an appropriate system. There's going to be URLs at the bottom of the slide, as there is this one, and those are blog posts that describe the topic in more detail. So I'm not going to worry about that in the future, but there you have it right there. Okay, so how do I know it succeeded? Well, here's what success looks like. We have our 19 scenarios, one line for each, from root 01 to tree 09 there. It says how many grace periods were done. This is a fairly short run. And the next thing in parentheses is the number of grace periods per second. In square bracket is some RCU flavor specific information I'm not going to go into. And on some of the scenarios, there's Nmax CBs, and that is a measure of how badly a callback flood affected the scenario in question. So in this case, the worst case was tree 03, and a callback flood generated a little over 1 million callbacks stacked up on a CPU. All right. And then really important is that if the test succeeds, you get an exit code of 0. So you really can feed this stuff to get bisect if you're crazy enough, and I have been from time to time. And have it automatically do stuff there. Okay, so that's what success looks like. But there's other things you can do. Dash kconfig specifies kconfig options. Maybe you want to run locked-up on all of them instead of on the few that normally get it just by default. You can also specify boot arguments. Maybe you want to suppress CPU stall warnings or something. You can run under KA-SAN, that's --KA-SAN or KC-SAN. However, with KC-SAN is really powerful. It finds all sorts of interesting race conditions, data races, and so on. But it requires very recent compilers. So, make sure you've got the compilers. It'll yell at you if it doesn't like the compiler you're doing and refuse to run, but it's you should take a look. You can also torture things other than RCU. So if you're annoyed at locking or SMP call function, or you want to do scalability tests of one sort or another on RCU and other things, use -- torture to do that. If you have a lot of CPUs or even a smaller number of CPUs, you may wonder, well, what can I get away with? How many batches is this going to take? And there's a dry run parameter with scenarios. If you do that, if you say -- dry run scenarios, it does not actually run the test. Instead, it prints out the batches it would have done and prints a number with each of them. So you can see how many batches are going to be required. All right. And so this is some things you can do to run specialized tests. Maybe you want to torture something, but you're not sure what. You just like to torture whatever you can torture. And the torture.sh script is there for you then. By default, this thing tortures a little of everything, all the options pretty much. This will take about 12 hours on a heavy-duty laptop. So it's maybe an overnight type of thing. And there's quite a few arguments to control this torturing. For example, you can say do everything. By default, it does everything except for kernel concurrency sanitizer, because compilers for it are kind of rare. Do all will say do that too. Do none says do nothing, which you can then follow up with these other sorts of things to enable different kinds of torturing. Okay, I'm not going to go into detail on these other than to say that on duration is kind of a funny thing. It's kind of a nominal duration, and 10 minutes gives you about 11 hours on 16 CPUs. Increasing it doesn't increase it that much. It does increase it, but the key thing is at that point you're dominated by build time. So decreasing it doesn't help much either. But it allows you to do more or less. I use this as an acceptance test. I run this a couple of times, and I especially run it before sending a pull request, just to kind of do a general check. I used to keep track of this in my head. There was some fun and excitement late last year that was very distracting, and I wasn't able to keep my head anymore. There were some embarrassing escapes, so I wrote this script. Well, maybe you want to use a debugger. In that case, --GDB is your friend. Here's an example where we said use all the CPUs. We want to torture the locking. we have to specify a specific scenario, lock 05 in this case, and tell it run the debugger. When you do that, it'll do a build, and then at the end, it'll say, hey, I'm waiting for you to attach a debug session. It'll give you the command you should run for that specific kernel. And then it'll also tell you what to tell GDB to get things going. So target remote :1234 and continue. Now, a restriction here is you only get to run one scenario. I just wasn't willing to put up with whatever would have to be done to allow multiple concurrent debugger sessions. And to be honest, I think you might be happy to run one at a time instead of trying to manage, say, 10 GDB sessions all at once. The big difference, you can use GDB commands, it's great, except using B or break doesn't work very well. Use H break to select hardware breakpoints instead. The thing is, the Linux kernel doesn't really like GDB rewriting its binary to insert software breakpoint instructions. So use H break. Okay, so that's useful occasionally. So you found a bug. Now what? Well, how about if you fix it and post the patch? Why not, right? Of course, life isn't always that simple. With RCU, heisenbugs are kind of the common case. And what that means is that before you can do much meaningful debugging in many cases, you're going to have to make the bug happen more often. This is more of an art than a science, but the next few slides will go through a few tricks that have helped a lot with me. One trick is really simple and really nice. You can adjust the CPUs, and adjusting CPUs can increase the probability of failure by a factor of M, okay? And one way to do this, and it depends on what the race is, if the race is between just random threads, then increase the number of threads by a factor of M, the number of CPUs in other words, it gives you an n-squared increase in the probability, but you have n fewer instances of results. So the overall effect is you get mx fewer runs with mx more CPUs each. That gives you roughly a factor of m increase in failure probability. On the other hand, if the failure is always between a particular pair of threads, so the RCU CPU, the RCU grace period K thread, for example, and some other single thread that's only one of in a given OS instance, in that case, you're going to be a lot better by having many small OS instances. Then you get a factor of m again by an mx decrease. And the diagram there kind of shows the theory there. This is theory, by the way. The real world does what it wants, but doing this can help work out where the bug is. If you make a lot of small OS instances and the bug probability goes up, that gives you a hint as to where the problem might lie. This actually is a special case of debugging things. The general case is you want to make risky operations happen more frequently. Okay, and by adjusting CPUs, we did that in a couple different cases in a couple different ways. CPU hot plug is a usual suspect for bugs. And so there's a boot parameter shown there that makes it so that we only wait 200 milliseconds between CPU hot plug operations. By default, it's several seconds. So if the bug involves CPU hot plug, that can increase the bug frequency by a factor, by also order of magnitude, excuse me. Okay, long-lived readers. Usually in the kernel, the readers are so short that if the grace period takes any time at all, nothing bad can happen. So RCU Torture goes to as much effort as it can to try to make very long readers, excuse me. It has to balance that out because if you have too many long readers, your grace periods don't happen as often, and that can also decrease your bug rate. So it kind of balances it. There are bugs that can only happen if RCU is spinning up from idle or going back down to idle. And so we do a full system idle in and out. That's the stutter parameter there. There's other problems only happen if there's massive piles of callbacks, and the forward progress thing causes that to happen. Now, in both these cases, and in the other one as well, the jitter one as well, the scripting does this automatically for you. You can use these to control it if you like something, if you prefer something else to happen. The other thing to do is we force vCPU preemption. And the dash jitter does this. We got the next slide, and one question that came up, I very recently popped on the matrix, so if there's people that had questions before I started looking, please feel free to turn your video on and yell them out. I'd rather have questions while we're going along. Nur Hussein asks if this would be useful for those of us teeny tiny test machines. Well, yes, actually. It's just that you'll be wanting to do things differently. So for example, one of the scenarios, Tree 03, wants 16 CPUs. But if you only have a 4 CPU machine, it'll take the 4 CPUs. It'll complain. It'll say, hey, you only gave me 4 CPUs, but it'll run. All right. So you'll still be able to do something. 4 cores, I don't know if that's 8 CPUs or 4 CPUs, but either way, it'll use what it can, what it has, and it'll run what it can. There'll be some bugs you can't find that way. On the other hand, those bugs can't occur on your setup anyway, so maybe that's okay. And besides, there's others of us that are running on large systems. And there's probably some bugs that only happen on small systems, in which case you'll find them and we won't. So I think it works both ways. Okay, so jitter. The way the jitter is working, what happens is we've got a hypervisor with QEMU KVM or whatever there. And we have RCU's torture scenarios that cover the CPUs. So if we had 12 CPUs and we had 4 CPU scenarios, we'd have 3 of those to cover all the CPUs. And then what we do is we run a bunch of jitter.sh processes. And each of these processes is going to randomly bind to a particular CPU randomly selected. And it's going to force preemption. It's going to spin for a little bit and then it's going to sleep. And the cool thing is that this is going to preempt the CPU even if it thinks it has interrupts disabled. And so injecting delays like this can force bugs to happen. Yeah, I agree with Elastomil, but if you ran 8 vCPU and 4 CPUs, you might increase latencies. But except for one thing, what happens? You could make that happen, but by default, RCU torture scripting, and maybe this is a problem that should be fixed. I don't know. Right now, the RCU torture scripting will say, "Oh, you've only got 4 CPUs, so I'll just run it as if it was a 4 CPU run." But that is an interesting point. It could well be that we need to have some way of overcommitting the CPUs. So that's an excellent point. All right. Another thing is if you're running a whole bunch of scenarios, by default, you run them all. And the bug tends to happen in a few of the scenarios. Well, just run those scenarios. And we saw --configs allows you to do that. There's a script, config.csv.sh, that will make a spreadsheet of the kconfig options and the boot parameters for the various different scenarios. And that can allow you to sometimes look and see, well, what's strange about these scenarios? Oh, okay, I see. And sometimes that points you right to the bug. But in any case, you can double down on the suspected accelerators, the things that are different about those scenarios, and specify kconfig options or boot parameters to make it more whatever the way it is. In some cases, I've had to modify the kernel or the scripts in order to really force things to happen more often. The other thing we do to make things happen faster, RCU torture does not run in user space. I mean, it could run in user space and it'd be in some sense more natural. The problem is that we have a whole bunch of overhead for each RCU operation, and we have no really control over what RCU does. We can't have long readers, for example, unless the kernel happens to generate long readers. So we don't do that. Instead, RCU is a kernel module. It directly calls the APIs, and it does rather strange and abusive things to try to force things to happen, which it can do in this mode. It would be very difficult to do from user space. Another trick is to enlist the aid of the laws of physics. Now, I wouldn't have believed this when I was much younger, but today, I'm sorry, the speed of light is just too freaking slow and the atoms are just too freaking big. And because of this, we have these memory latency and NVDIMM effects that cause us so much trouble. Okay, well, if there's trouble, when I'm testing, I want trouble, so let's enlist the trouble. And a quite recent change to the RCU's torture scripting is that it places the RCU torture guest OS CPUs to maximize difficulty. So we take 2 CPUs and we put them into one core, and we take the next 2 CPUs and put them in another core, preferably on some other socket. And what happens then is that the latency between the CPUs in the same socket is much, much less than between different socket. And as Blasmil pointed out, the changes in the latencies can cause additional bugs to appear. And for certain types of races, this can happen. I did this fairly recently, and the effects were not subtle. I don't have time to go through the things, but the URL at the bottom goes through one of the strangest bugs I've come across. RCU CPU stall warning times are set to 21 seconds. Once I made this change, I was getting 2,199.0 second RCU stall warnings occasionally, but always that number, as in the difference in time was in the tens of milliseconds and a small number of tens of milliseconds. That took me some time to track down. It was quite entertaining, but we don't have time for that now. Of course, if you're going to torture something, you need to know what it's supposed to do, and that's where semantics can come in. This is a graphical representation of RCU semantics, which are rather simple, actually. So if we look at the upper left-hand corner there, over here, we've got RCU read unlock, the end of the read side critical section happened before we freed the memory, in which case it's okay if that read side critical section saw the memory that was to be freed. If we go over to the right-hand side, in this case, we've got a case where RCU read lock started after the removal. That means the read side critical section can't see the stuff that was removed, so it's okay for that read side critical section to extend past the point that stuff that it couldn't see was freed. In the lower left, we have the belt and suspenders approach, where we both couldn't see the memory removed and we weren't around when it was freed, and that's perfectly fine as well. What's bad is in the lower right here. If we have a read side critical section that saw the stuff that was removed and was still hanging around after it was freed, that's really bad. That's a bug in RCU. That'll cause all sorts of horrible problems. You just don't want that happening. Okay, another way of looking at this is from an API viewpoint, and we can also state these semantics very simply. An RCU grace period must wait for all pre-existing RCU readers. And this, I'm not going to go through it line by line, but this thing really does work in the Linux kernel. It implements RCU, or at least a portion of the API. It's in RCU torture. RCU torture tests this thing from time to time, the trivial scenario. As you can see, the readers are very lightweight, and the update is very simple. So, why not do something simple? This is simple. We like simple in the Linux kernel. Why not do this? Well, unfortunately, this is the Linux kernel, and so there are a few complications. This is what fit on the slide. This is by no means an exhaustive list. Each of these things is worth a few hundred lines of code, maybe 1,000 lines of code. What I'm going to do is I'm going to focus on the last one, just to talk about something definite. RCU should avoid exploitable ease of use issues. And it turns out this is no longer a theoretical possibility. There was a LinuxConf AU presentation on it a couple of years ago. And what it was is I used to think that RCU was so low level that it wasn't hackable. And I've since, when Rowhammer showed up, I started deciding that wasn't the case. And then when this thing showed up, I knew it wasn't the case. But the effect, the relevant effect for this presentation, back in the old days, there were multiple flavors of standard RCU. There was the thing with RCU read lock and RCU read unlock, and you use synchronized RCU to wait for that. And then there's preempt disable and preempt enable, and you use synchronized sched to wait for that. And another example over here, there was also BH disable and BH enable, and you used synchronized RCU BH to wait for that. So you had these three independent flavors of RCU, and you had different update size to wait for them. Unfortunately, the exploitable problem was somebody using the wrong wait with the read side, and that caused all sorts of problems. In some sense, this was their fault, not mine, but Linus, to his credit, said, "Hey, Paul, can you make this not happen again?" Which it took me a year, but I did. And so right now what happens is that all of these different readers are the same thing. So you just do synchronized RCU and it waits for all of them. And that means it needs to keep track of the overlapping things. So yeah, we have a reader started here and ended here, except we had one starting here, so we have to wait for the whole thing, all right? And likewise, we have three of them overlapping, we have to wait for the whole thing. We have to kind of flatten it into one reader. And that means our RCU torture must randomly generate overlapping readers, which it has for some time. I realized that was a vulnerability. I put that in at the time that I made this change, except that I forgot something. I forgot to include just nested RC read lock readers. And I actually added that this week. There were a number of really embarrassing bugs that had slipped by. They were in you had to work hard to get them. So I don't know that anybody's seen them in production, but still, if you don't test it, it doesn't work. I think I fixed those by now. We'll see how it goes. Actually, I've got one I'm still testing. So in short, if we look at that simple implementation a few things back, was like less than 20 lines of code. That's kind of like the little puppy dog there. It's cute, it's elegant, it's wonderful, it's warm, it's soft, it's friendly. What's not to like? Well, what's not to like is this poor thing's just not going to survive in the context of the Linux kernel. It just doesn't stand a chance. The Linux kernel is going to run right over it without even knowing it was there. If you want your synchronization primitive to survive in the Linux kernel, a little puppy dog isn't going to cut it. Instead, you need something like this, okay? This might have half a chance of surviving the Linux kernel. So what that means is the semantics, the semantics we expressed, and it can be expressed mathematically, has been. We did a bunch of us did a 2018 paper expressing them that way, with executable formal semantics. But that's just the tip of the iceberg. There's a whole pile of other stuff underwater, not visible to the mathematics, that has to be dealt with as well. Now, you could interpret this as me dissing the formal verification people, and to be quite frank with you, there's a fair number of them that certainly deserve some serious dissing, but that's not really my intent here. Not this time anyway. The key point is that this is actually an improvement. A few short years ago, this entire thing was underwater. There were no formal semantics for any part of RCU. It was all informal. So this is an improvement, a significant improvement. And who knows, maybe a few decades from now, we'll have most of the iceberg above water. I'm not sure I'll be alive to see it, but that might happen. Here's hoping that enough formal semantics people take this sort of thing seriously and they make this sort of thing happen. There's also a software engineering viewpoint. And the key thing here is that RCU software, it's got some number of lines of code. There's industry statistics that, quite frankly, from watching myself program for more than 40 years, 1 to 3 bugs per 1,000 lines of code is pretty good for me. Now, you can do better. I've seen a project that did, I kid you not, 0.04 bugs per 1,000 lines of code. That's 1 bug per 25,000 lines of code. But this was a safety critical application. They had extreme code style restrictions, and it was single threaded only. They used formal methods, the whole show. And even with all that, they had way more than 0 bugs. Another thing that should be of some concern is that RCU changes. And so the median age of a line of code is less than 4 years. This is one of those rare circumstances where old stuff is more reliable than new stuff. What this means is that we know that there's a few tens of bugs in the Linux kernel RCU. They're in there somewhere. You don't know where they are, but there are bugs there. Now, you remember that successful RCU torture test I showed you near the first of this paragraph of this presentation? That was not a success. That was RCU torture failing. We know that there are bugs remaining in Linux kernel RCU, and that RCU torture run failed to find them. So at every point, there is a first-class bug, either against the software under test or against the test suite. Let's look at it from an installed base viewpoint. That's bad enough, but it's even worse. I'm going to use my experience. My first, I guess, sort of professional software effort, pro bono, was for the National Honor Society in 1975, when I was a senior in high school. It was a computer dating program. If we had a 1,000,000-year bug in that, it'd take 1,000,000 years to find it. As it turned out, we did have a bug. I was made aware of it when a very irate senior girl came complaining bitterly about the fact that she'd been assigned 4 freshman boys as her dates, despite the fact that she'd indicated a strong preference for upperclassmen. In retrospect, it might have been a mistake to allow the data entry to be done by the freshman boys, but live and learn. John Grove suggests rewriting RCU in Rust. Well, I've asked questions many times, actually pointed in that direction. I never get answers. So you guys answer my questions and maybe we make progress on there, okay? But if you're gonna ignore me, I'm gonna ignore you. Good luck. Again, everything can happen will, maybe in geologic time. Murphy's actually kind of a nice guy if you only got one instance. The number of instances I went on increased. I was doing process control stuff in 85. Sequent, we had 6,000 systems. We're still, a million-year bug doesn't happen very often. I don't know how many instances of 2005 Linux there were, but call it 10 million. At that point, we're having this million-year bug once a month across the installed base. And well, at this point, we're certainly not leaving the bugs to our grandchildren, unless our grandchildren are already live and already coding and debugging, in which case, well, maybe we are. But or if we have grandchildren very young. Smartphones showed up. Suddenly, we're getting million-year bugs several times a day. In 2017, a gentleman from ARM told me that there were 20 billion instances of Linux in the world, and that was billion with a B is in 10 to the 9th power and 20. At that point, we're doing it several times an hour. And, it could get worse. If the Linux kernel even gets a small fraction of IoT, we could be at 1 trillion, no problem. And at that point, I got a question. Has Murphy transitioned from a nice guy in 1975 to a homicidal maniac in, say, 2025? Now, I don't know about you guys, but I would feel really, really bad if my software killed somebody. So this is a matter of some concern to me. So this has kind of been the bad news. Maybe we should try something else. Natural selection is, it's certainly done an incredible job of making some really strange things happen in living things, both good and bad, but still very complex. Of course, no discussion of natural selection is complete without a photo of the great man, and there's Charles Darwin to look over the proceedings. And the thing is, this was living things, but as we've since learned, these living things are governed by DNA, which has sequences of amino acids grouped into 4 amino acids per codon. So what Charles Darwin was seeing was natural selection of software of a sort. So if Charles Darwin's natural selection applied to software, why don't we do it with computer software? So let's give it a shot, right? Some of you may object to the upper left-hand box where I'm accusing you of randomly generating your software, but I've been at this for more than 40 years. If you want me to characterize your work differently, behave in such a way to prove that characterization wrong. Have at it. But randomly generated or not, we apply a validation suite that does our selection function. It generates bugs. We fix them and hopefully inject fewer bugs than we fix. If we do that enough, we should end up with robust software dropping out the bottom. What could be better? There is, of course, a problem with this. You see, natural selection applies to software. Guess what? One type of software is a bug. Therefore, we don't end up with just robust software out the bottom. We end up with the software and also bugs that have adapted themselves to our validation suite. This is also not a theoretical issue. Some years back, I got a report from a guy in Russia saying, hey, I'm running a heavy workload and I'm getting RCU errors. And I looked at his stack trace and it was pretty clearly RCU at fault. So I asked him for his .config file. Silence. A few months later, I got another report from somebody in Australia who also was heavily loading their system and getting the occasional RCU problem. Also, the stack trace showed it was pretty clearly RCU's fault. Great, can I have your .config file? Silence. For a couple of weeks. Then the guy from Australia comes back. He's generated a huge, this is before tracing we have today, made this tracing infrastructure trying to find a deep, dark bug in the guts of RCU, and instead it was just a stupid initialization problem. What happened is if CPU hot plug was disabled, RCU would decide there were no CPUs. And so when you said start a grace period, it would just click through a state machine, taking a fixed period of time, about 3 milliseconds, or 3 jiffies, I should say, waiting for no CPUs to get done. And so if you had a really heavy load, that was a problem. The thing was, I was testing that, except that there had been the addition of hibernation and suspend resume. And hibernation and suspend resume were enabled by default, and they selected CPU hot plug. So I had not been testing CPU hot plug and whittling for quite some time. That was a hole in my validation suite, and a bug adapted itself to it. So, you know, we have to do something more here. We have to take bug reports such as that one and improve our validation result. And yes, right now, RCU torture, if the kconfig, if the .config file comes out differently than it expects, it screams as a result of this experience. But even this isn't necessarily enough. I mean, this helps, but it's not enough. You see, normally, you validate only your intended use case. Only a few of us crazies validate things we don't expect to happen. And that means you do a major development, you generate a whole bunch of bugs, you validate them, you fix those bugs, and you end up with some bugs left over that nobody cares about, maybe. And then you do more development, you fix more bugs, and then you end up with more use cases that are excluded because there's this wall of bugs preventing your software from addressing them. So in some cases, you don't have any choice. You've only got so much time and effort, and clearly, if you only got so much time and effort, you should prioritize the ones affecting your current users over bugs that might affect somebody that isn't there yet and might affect nobody. But if you have the luxury, you should go a little further. And so I add paranoia to those bug reports. And it turns out that the fuzzers, Trinity and Syscaller, for example, are actually pretty good at this, at finding things we haven't imagined. And both of them have found bugs in RCU. So, you know, good on them. So natural selection might help us, but it's important to realize that natural selection is kind of this funny euphemism. And to understand what that means, I invite you to consider what happens to individuals who are not selected, okay? Not quite so pretty. The key point for us, though, for software, is if your tests are not failing, they are not helping improve your software. All right, so this is why tests tend to kind of become less effective. What happens is the bugs adapt to those particular tests. Unless those tests are maintained and developed as well, they become obsolete and no longer help you. All right, so the price of robust software is eternal test development. So in summary, we've talked about torturing RCU. We've talked about using GB as an example. We've talked about how you can help track down heisenbugs. We've talked about the role of RCU semantics, perhaps more limited than one might hope, but still there. And we've talked about validation, including the good, bad, and ugly of natural selection. So what I'd like to do is I'd like to come full circle. I'd like to end this presentation where I started it. I'd like to call for a round of applause for testers, because without them, our software would not be anywhere near as robust as it would be. But this time, I'd like to focus on one specific group of people that have tested software. I'm talking about these guys. These guys are hardcore. You do not want these guys angry at you. I mean, yeah, sure, you know, they torture the software with new workloads, so they probably stress test it for all I know, but that wasn't enough for them. You know what these guys did? You know what these guys did? They banished the software, banished it to Mars. So with that, that's the end of my material. I've got a couple things here, a couple slides with more information. The first slide talks about tricks I've learned over 30 years of validating software. And RCU in particular, of course, but also concurrent software in general. And then the RCU specification, which is a function of time, some things about my experience with that. With that, if there's questions, comments, thoughts, suggestions, bug reports, fixes would be even better, you know, have at it. Just go ahead and enable your video and talk. I don't see any new stuff in the chat. And I do appreciate the virtual applause. Thank you very much. And I'll admit I miss face-to-face presentations, but hey, I also want to thank the people that made this possible. getting this stuff working is not easy, and it's a learning process, and there was a lot of work there. So thank you guys for making this happen. And thanks to the rest of you, all of you actually, for your time and attention. And hopefully this helps you do your own software and helps you find bugs in my software, or maybe even fix in my software. I'm not proud. Well, if there are no questions, I'll hang out here and for another 5 minutes until we start the break. But here we are.
Cool. I think I have, wait, let me turn on the video. I think I have a not very technical question, I guess. Like, how do you, because you said like you worry about your software killing people, not literally, but
literally. I mean, look at what Linux is used for. And those SpaceX rockets, those got x86 CPUs running Linux, my friend.
Do you still, I mean, still when you discover a bug in RCU, for example, it's just something that you go and fix, right? It's not something that you really worry about.
Well, that's a good point. The thing is I could flagellate myself, and sometimes I do. I mean, there was a bug that that hole in RC Torture wasn't testing nested things, found just a really, really stupid set of bugs. And yeah, I kind of beat myself up, but and that's good. It kind of emotionally prepares you to think harder. You know, it's too easy to be overconfident. Yeah, I know how this works. I'll just do this. It'll be great, right?
Right.
And you have to have that overconfidence, because otherwise you'll never do anything.
Yes.
But at the same time, you have to kind of punch it occasionally.
Yes.
Yeah, because you do have to actually, yeah, I might have made a bug. I do need to write tests. I do need to hammer this hard. And so there's a balance. If you do too much self-flagellation, you'll just be self-flagellating, you won't get anything done, and then you're no good to anybody. Okay. If you never do any, then you're probably at least inflicting bugs on people, and possibly much worse things.
Yes.
Good question, though. It's a hard balance to strike. Gotham Shinoy asks, how do I ensure that RCU Torture has no bugs? And it's a piece of software. It's got bugs too. So there's, and in fact, it has had bugs. One of them I described, where I was testing overlapping read-side critical sections, but failed to test nested read-side critical sections. Back in the day, before a few years ago, there wasn't really any kind of bug you could have in that arena. But task trace RCU, and it, oddly enough, tiny SRCU has one. Now, I could argue the tiny SRCU one is a locked up false positive, and I'll be sending a patch out later on that. But RCU Torture can have bugs. It can have bugs where it gives false positives, where it complains about things that aren't real. It can have bugs where it misses things. One thing I did a while back, I worked with some guys at Oregon State University. Thank you. And what they did was they did mutation testing. What they did was they had a program that automatically generated mutations of the RCU code itself. And then they ran RCU Torture on it. They did a bunch of other things. For example, there's some changes you make that don't change the binary, so they checked for those. And then they would run them. They build first. If it got a build error from the change, it said, great, the suite caught that. If RCU Torture complained in 2 minutes, they'd say, yep, great, RCU Torture got that. The ones that survived, they ran for a little longer. And the ones that survived that, which there were actually fairly few, they've handed off to me. And it was my job to take a look at the bugs, the changes, and say, no, that's not a bug, or that is a bug. And they did find some bugs in RCU Torture as a result. And some of those bugs were, in fact, hiding real bugs in RCU. So they can happen. That's one, that was kind of a tour de force. I don't see doing that all the time, although I have known some projects where the maintainers said they were going to do it periodically, and good on them, right? That's an excellent thing to do. But yes, there can be bugs in RCU Torture, just like there are bugs in RCU, and we have ways of chasing them, and it's not perfect either way.
Did projects like RCU Torture and, for example, LogDep start because you had there were bugs and that needed to be fixed, and weren't supposed to be regressed, or was it paranoia from the get-go that that people said, okay, we need something like LockDep and RCU to just be on the safe side?
In the case of RCU torture, there was a thing called TLB test back in Dynex PTX days, and the problem was that that was kind of both. As I developed RCU, there were bugs, and it's kind of like, if there are bugs in this thing, it's going to be really, really hard to find them. They'd look like memory corruption. And so I extended TLB test to cover RCU. And then by the time we got to Linux, I knew it was needed, so I made one a few years after it got accepted. LockDep, I think I was not one of the people that started LockDep, although I very much appreciate it and use it heavily, and it's great. But I'm pretty sure that was there because we're getting a lot of deadlocks, and we wanted to find them more quickly. Bruno Larson asked if we thought about automating natural selection, adding mutations to the test cases, kind of like smart fuzzing. And actually, you can think of RCU torture as doing that a little bit today. It uses a lot of randomness. So it'll randomly decide how long a reader should be. It'll randomly decide what operations do in what order. But the fuzzers, Trinity and more recently syscaller, really do take that to an extreme and do that a lot more. The stuff they do doesn't apply to RCU. I mean, what the fuzzers will do is they'll grab an open call and feed it random garbage. The problem is that the RCU's APIs don't have much possibility of doing that sort of thing. I mean, RCU read lock doesn't take any parameters, so what are you going to do, right? RCU assign pointer takes a pointer, and if you fuzz a pointer, you're probably testing your exception handling more than RCU. But nonetheless, we can fuzz the timing of the calls, and we do that. So that's an excellent thing. People do it, and it probably could be done more. Dave Hansen says the LockDep, as far as you knew, was a problem of people being tired of chasing deadlocks, essentially. And so yeah, I believe you, Dave.
Cool. I think we're at the end of the talk, and you can continue this discussion for a bit because we have a 15-minute break, and we'll continue at the full hour, or you just move it into a hack room if you want to keep on discussing. Okay. I'm open either way. I have some time after this, but up to you guys. Yeah, and there's the dark side of tests. They give false positives or otherwise cause annoyance. Or you may want to get things kind of sort of working, and you might want to defer some bugs, but no, you're getting test reports saying, hey, here's a problem, right? Well, I know there's a problem there. Haven't got there yet. But overall, I think it's a good thing. James isn't happy about LockDep, it seems. Tell us what you really think, James. Come on. And a lot of people aren't happy with the kernel concurrency sanitizer, but I like it a lot. It's found a lot of bugs for me. It's really cool. It finds false positives too, but I'm willing to take those. Go ahead, James.
False positives are becoming the bane of our lives. The more testing we get, the more false positives we get. I can foresee a time when we'll spend all of our waking hours dealing with just false positives, and there won't be any real bugs left in the universe.
And I guess what that says is that we should be working to try to automatically classify or get rid of the false positives. There were some changes to LockDep to reduce false positives. And RCU uses them. There's by default, the combining tree, the RCU node tree locks would give me LockDep warnings all the time. But there's an API, which I don't remember the name of, where I can say, hey, even though these locks look the same, I can make the layers of the tree be in different lock classes. So if we're having false positives, there's some way we can make LockDep recognize those. There's a false positive I came up with this morning. In SRCU of all things, tiny SRCU. It's saying, hey, if you have two CPUs, this deadlock can happen. It's like, but I've only got one CPU, otherwise I'm not running tiny SRCU. In this case, it's okay because, quite frankly, I can break the deadlock by getting rid of a class of false redundant wake-ups. So I may as well just fix it that way, but I can see where that could be annoying. Go ahead, James.
Well, I was going to say, I think the key point is to ensure that you have more actual cases than you have false positives, and you're reducing false negatives. It's a bit like spam processing. If you look at crap mail services like Hotmail or Outlook, which basically just rejected all of the Linux Plumbers mass mailing lists, it's the false positives that really kill you. Once you get beyond a certain level of false positives, the service becomes useless. And we have to make sure with all of testing and fuzzing things that we don't reach that point. That's the point at which developers tire of them, they turn off the service, because basically you're drowning in false positives and you don't have enough real signal to make any headway with. I mean, technically that's what happened with coverity scanning the kernel.
So that's an excellent point. That's an excellent point, but I'd like to apply another level of nuance. And I want to pick on kernel concurrency sanitizer. Because there's been a lot of complaints about kernel concurrency sanitizer false positives. Now, in many cases, I think that the developers are just not appreciating what compilers can do to them. But still, as you say, if it causes them enough trouble, enough perceived trouble from their viewpoint, they're going to turn it off. So what we did in that case is, by default, what we did is we listened to them, and to the extent we could, we had kconfig parameters to allow shutting off the complaints that they consider false positive. For example, if you rewrite a variable with the same value it had before, KCSAN used to complain about that. By default now it says, it's the same value, there's a write, but nobody can possibly notice, so forget it, we're not going to worry. All right, and so by default there's a bunch of things it doesn't warn about. Now for RCU, to your point, I'm willing to take a 20-to-1 false positive rate, just because the real bugs are so damaging in RCU. Okay. Now, in SCSI, maybe it's different, or in HPEA, maybe it's different. That's fine, me versus you, and we should be able to make a different choice. So Marco gave me a KCSAN_strict kconfig option, which I set in RCU torture. And then I ignore the reports from the rest of the kernel. Not automatically yet, but to your point, I'll have to get there at some point, because I have to manually look at them. But I think that what we have to do is be able to adapt the tools to the because if you have a really high severity bug, a high impact bug, a higher false positive rate is justified. If the bugs are low impact, then you want to pay a lot more attention to your false positives, and it may vary from subsystem to subsystem. Go ahead.
Yep, I agree with what you said. I mean, I'm not advocating we have to get rid of all false positives before we find the test useful, but we have to get the false positives under control. Even for you, yes, there is a rate of false positives beyond which you will find the test useless.
Yeah, 100%. For one thing, if it's only false positives, not helping me, right? So yeah, it's an excellent point. It's difficult. It's going to vary from place to place, but I think what we're saying is that in the testing phase, we may have gotten to a point where we need to put some effort into reducing false positives for some of the popular test things. Okay, if there are no more questions, thank you again for your time and attention, the questions and discussion. It was really great. And, have a wonderful rest of the conference. And, see you guys in later sessions.
Thank you, Paul. We'll be having an 8-minute break. We'll continue, I think around whatever it is in UTC, at the full hour. With our final talk in the referee track today. Rick will talk about protection key supervisor in a bit. So until then, we'll take a short break.
It's 1700 UTC, by the way.
Thank you. Let me put on the default slides. Okay. Ira and Rick are both here, I think, right? Yes. Who wants to be made presenter?
I was going to take the presenting.
Okay, then
I haven't shared my camera yet in the conference, so let me see. Oh, hold on. I need to allow that.
I'll make you a presenter then.
Okay.
Okay, I don't.
Let me move this.
I can give a very brief introduction. Ira and Rick are going to be talking about protection key supervisor, and you're free to take it.
Okay. Yeah, I'm going to talk about supervisor memory protection keys, but we call them protection keys supervisor, or PKS for short. That's the name. Oh, okay. Here's the next slide button. Sorry, I was a little distracted there. So quick outline, why are we doing this? We're going to explain a little bit of the hardware overview first, because that helps to go through some of the use cases, and then we're going to present a couple of use cases and then circle back to the core software and close out with status, next steps, and acknowledgements. And I'd just like to say right from the get-go, I had a slide in here about testing. So coming off of the previous talk, I took the slide out, but I kind of feel bad that I did, because that last talk was so good. But anyway, we do have test case for this, but we won't present it here. So, why are we doing this? We have a couple of use cases. Specifically, persistent memory stray write protection was one of the cases that was in the back of our minds when Intel developed the hardware for this. And subsequently, we've found a couple of other good use cases. There's been a lot of different use cases batted around and discussed. IBM was even talking about some things that they were looking at, Mike Rappaport. But right now we have two use cases that are in development. The stray write protection, which we're submitting as part of the core patch set, and then the write protected page tables that Rick is going to present that he's been working on. We've also submitted to the mailing list another use case for hardening sensitive data like kernel keys. We've kind of backed away from that use case. It's a little simpler, but we're focusing on the first two. So, one of the things about these use cases is, one might say, well, why don't we just use the page tables, specifically write protected page tables, you can write protect things using the page tables themselves, but we're going to kind of get into that. So to give a little bit of background, the PKS hardware implements something very similar to protection keys in user space. So PowerPC and x86, AMD, Intel support a user space protection key mechanism, and PKS extends that to supervisor page tables. So a protection key is added to each page table entry, and there's a model specific register, MSR, that is per thread that defines the actual access allowed for each of those protection keys. The changes to the access are, quote, fast. And I put fast in quotes because obviously writing to an MSR is not always the fastest thing. But when you compare it to page table walks or having to flush TLBs, and the fact that the MSR is non-serializing, so it's actually a little faster than a normal MSR write, and the fact that this is a thread local mechanism, the changes to the access is a lot faster than updating traditional page table protections. So getting into the details, here we see a simple page table entry, and we have the execute bit, we have a user and supervisor bit and a read write bit. PKS adds the protection key. It's 4 bits that define the protection key in some unused bits. It's available in 4 and 5 level page tables. So x86 64 is all that's implemented to support right now. And there's a per thread MSR that defines the actual permissions that are allowed for each of those 15 P keys that are allowed. It is a 64-bit register, so we have some bits reserved. Right now, the hardware defines an access disable and a write disable bit for each of 0 through 15 P keys. P key 0 is reserved as part of the default. These bits are defaulted to 0, so normal pages that exist in the kernel today will just pass through with full access. So we use one of those P keys just for what I'll call normal pages, and that leaves 15 P keys for users like our use cases that we're presenting here. It's important to remember that this is a thread local register. So each CPU has this register, and changes to this register affect only the thread running on that CPU and not other threads. This is very important for a number of reasons. It's both good and bad, as we'll get into later as we explore the use cases that we had. And it's not Xsave managed. So as threads are swapped in and out, the MSR needs to be preserved in software. A final note about this is there is no execute protections. This protection is layered on top of the existing page table entry protections. And so, but execute is not one of the protections that is layered on top. So you can do read write, write only, and full read write only, and access disable, which basically allows no access, but you cannot use like an execute permission bit. So the advantages are, of course, that this overlays additional protections on large pages of domain, or on large domains of pages. And by that, I mean you can, rather than twiddling the bits on a single PTE, and yes, PTEs can cover large pages of different various sizes all the way down to the 4K page. However, by setting the same P key on a lot of PTE entries, you can change the protections on the large areas very quickly, because you can do this MSR write relatively fast, and that protection applies only to that thread and can be turned on and off very quickly for an entire domain. This really helped, as we'll get into with my stray write protection use case. And the changes are thread local. So the page table entry is constant in the P key, or in the page table entry P key is constant. It stays the same, and the protections available through the page table entry are preserved. So, as some people might see right away, there's this stray write protection. So the issue with persistent memory is that persistent memory, and actually all memory, is vulnerable to stray writes. Persistent memory is mapped in the direct map, but we really don't want just any old device writing into this memory. But more importantly, one of these stray writes could permanently corrupt user data. So take, for example, a file system that's created on top of a persistent memory area. If you were to have a stray write to some of the metadata of that file system, the file system could become permanently corrupt and corrupt a large swath of user data. This is really bad, and we want to prevent that. And changing page table entries is troublesome. Obviously we could, very carefully map persistent memory with page tables in a way that we could potentially twiddle bits, mapping large pages or some such thing. But that's going to be very troublesome. And PKS is fast, and like I said, we can map these large domains under a single protection key and twiddle the protections very quickly. So it turned out, though, that was kind of our general design idea when we did this, but it turned out that applying the PKS protections was really easy. So when we set up the page tables for persistent memory, it's very easy to just pick a P key, assign that P key to all the page table entries, and we're off to the races. And we thought toggling protections was going to be easy as well, because there's very few places where drivers actually need to have direct access. But it turns out it was kind of hard. Get my button here. So the default is that restrictions are no reads and writes, which basically prevents any stray write, any random driver from writing to our memory through the direct map. And it works well for the default PKS permissions for the stray write. Direct access is limited, and like I said, there was just a few drivers that needed access directly, and we thought that general kernel access being wrapped with KMap would be very easy to enhance the KMap interface to twiddle the PKS protections on a thread basis. And it turns out the KMap didn't work out quite as well as we thought. The big thing was the KMap was not thread local. Like I said, I kind of stressed earlier that PKS, the MSR register, is a thread local register. So global updates became a difficult thing to do. Initially, I tried to modify KMap to create a global update across all threads, all MSRs, and you know, did some things in the fault handler and some other things, and it just turned out to be really difficult. And it was brought up on the mailing list in discussions that if we do that, if we do have a KMap that basically maps something globally, effectively we're kind of turning protections off, and a lot of drivers that do these types of KMaps often leave that KMap in place for a long time. So effectively we're kind of turning the protection off anyway, because everybody else is just gonna have open access. And it was decided that it would be better to actually fix KMap and start to restrict the uses of KMap. Specifically, it was decided, you know, KMap was never really intended to be used that way, and people that are using it's kind of a violation of the semantics of KMap, you know, even though it's not technically wrong. And obviously people have just sort of like, it's evolved into being okay. So initially I had a KMap thread, which basically took KMap instances that were thread local and basically turned them into, you know, kind of a well-known, we can support PKS. We know that we're only doing a thread local operation here. So the user can call this KMap. It is technically a global mapping in my implementation, but it would do the PKS correctly. That was kind of one step, but then Thomas Gleixner came along and said, you know, what we really want isn't what you're doing. What we really want is a KMap local page. What we want is a preemptible thread local KMap, which is what KMap was really intended to be all along. And so he came along and wrote the KMap local page patch set, which actually created a preemptible thread local mapping. And of course, that works great for me for PKS. So once that patch set landed, I was able to start to convert the users that I was really concerned about into the KMap local page and drop my KMap thread patch. Now, this all kind of drove the need for a relaxed mode, because as we started to comb through the kernel and look at all the KMap instances, we realized that, you know, there's still some people calling KMap, and, you know, we believe at this point with the current patch set that the users that are going to be using persistent memory aren't going to be calling KMap. However, that said, it's possible that somebody will call KMap. And so if they call KMap, we needed a relaxed mode. And so we're going to discuss that a little bit, but we're going to segue first and let Rick talk about his use case, and that's going to feed back into that need for a relaxed mode. So go ahead, Rick.
All right. So I think Ira, I don't have the ability to change slides, so I'm just going to. Oh,
I made you a presenter just now. You should have the ability to change slides now.
Oh yeah, I see it now. Thanks.
Thank you.
So yeah, I'm going to talk about another usage I've been exploring, which is this write protected page tables concept. It's something that is still kind of being proved out. I'm kind of just exploring it with these RFCs in public. You know, it started out with hardening in mind, but other people brought up that it also could be useful for debugging as well, since corrupted page tables can be especially hard to debug, makes for very strange stack traces. The general idea, though, is that to protect corruption of the page tables by making them read-only and only writable when they're on a per CPU basis when they're being modified. Unlike PMEM, this usage of PKS wants the PKS memory to have a default read-only permission, because we're only worried about the stray writes. So this required IRA to do some work on the core series to support not disabled default values, so that when you have an interrupt or a new thread or something, that automatically gets set with the what the default value will be. And as Ira mentioned, toggling read-write permissions with PKS memory is easy and fast. And for page tables, the toggling of the PKS protections is actually, it is easy. There's just some page table helpers, and we just toggle them inside there. You can see on the slide some examples. But in sort of the opposite situation of what Ira had to deal with for PMEM, is that the toggling is easy. We don't have to deal with the KMAP stuff, but applying the PKS protections is a little more complicated, because the page tables are allocated dynamically, unlike PMEM, which is allocated at boot. So PMEM, the usage will apply the protection, when it maps, but the page tables are allocated dynamically at runtime, and these are just coming from the page allocator. There's not like a lot of rhyme or reason to where they're going to end up. Let's read the comments. The problem with just sort of with applying the protections at runtime is that changing the direct map is pretty expensive. Since the kernel address space is shared, of course, you need an all CPU TLB shoot down. And on x86, it also will break the direct map down to small pages or whatever size is needed, and then that's never repaired. So you end up with if you just the naive solution of just, okay, we allocate a page, now apply PKS protections before we start using it, I didn't even try to implement that. It just seemed like it would never work. This is sort of, and this a problem of breaking the direct map for applying permissions on it is sort of a general kernel memory permission problem. But for this usage, for modules and stuff, there's not that many modules. But for page tables are allocated way more frequently, so it just would never work to just sort of start shattering the direct map all the time every time a page table gets allocated. So like I just said, it's not the first thing with this problem. There's been some attempts to sort of work on it. Personally, I've done a bunch of little experiments around the other kernel memory permissions, mostly modules and BPF JITs. And then there's also those were all just nothing ever made it upstream. But there's the secret mem feature, which does a similar thing. It's not applying permissions exactly, but it's unmapping pages, which I guess is sort of a permission. And those, these all sort of use a similar approach, which is to sort of convert memory in batch. So you sort of amortize the cost of the shoot down. And then you want to also convert memory in physically contiguous regions so that you don't have shattering of the pages all across the direct map. You sort of localize all the breakage. So what we have so far in the PKS table series is just a simple this group page cache thing, which has per node caches. And when the amount of page tables grow, it tries to allocate from 2 megabyte pages and then converts them to PKS and then starts using them and zeros them, of course. The other thing we've added is a shrinker so that you don't end up with just a giant cache of page tables. Eventually, if the amount of page tables in use shrinks, the system can ask for them back, and then we just reset them to their default permissions before returning them to the page allocator. And it seems to work okay. The one downside or one downside is that we can't return, today page tables when they're freed are just returned directly to the page allocator instead of, but what we need to actually make sure we return them to this group page cache thing, because if we return permission pages to the page allocator, the next user is going to be unhappily surprised when they try to write to it. So there's some extra logic in the page table handling code in the kernel to make sure we return it. If it's, like in swap, it has to say, well, if this is a page table, let's make sure we return it to the page table place. The other sort of interesting problem, complexity with this thing is handling the direct map page tables. So that's like the page tables that are mapping the direct map. If the kernel runs out of page tables, then it needs to convert some more to PKS, which usually requires breaking a large page in the direct map, which would requires a page table, but the problem is we don't have any, so we're kind of in a chicken and egg problem where we've ran out of page tables and we can't make any more. So looking at this, I looked at a couple options. One option would be to convert a high order page and use it for the requested page and for the direct map split. This would require a high order page to be available, so it regresses from the existing behavior a little bit. You can't get two pages, scattered about and pull this off. Sort of get a net profit of PKS protected page tables. But it also leaves a window where the page table is unprotected right before it gets installed. So for the hardening usage, this is not ideal. Now, a simple option would be just to map the direct map at 4K at boot. And this avoids never ever needing to map the direct map, or to break the direct map, which simplifies a lot of things. But mapping the direct map at 4K has undesirable performance characteristics. So what we have for now is something where it reserves enough page tables at boot or at hot plug to map the entire direct map at 4K, and sort of sets them aside, pre-converts them to PKS, and then so then it can just, when you need to break the direct map, it can never fail. It always has a PKS table on hand to break the direct map. And that, the downside is that it has the same memory overhead as mapping the direct map at 4K. But at least you don't have to have, you don't have to take the TLB page walking performance hits. So this is the current solution. So I think maybe there's some better way where we can have it all, but I haven't figured out anything better yet. So that's what we have for now. And then I think next is back to Ira.
Okay, let me give you the presentation link. Okay.
Yeah, so obviously I was pretty focused initially in the core software on my use case of the stray write protection. Rick's use case coming online really helped to kind of redefine some of the core software support. Specifically, we mentioned the default values that are required. Obviously, stray write fit in very nicely with the defaults for all of the keys, which is no protection, or which is no access. And that worked great, and it seemed like having a dynamic key allocator would be nice because we're just allocating keys that are unused. But it turned out, again, because of that global update difficulty, allocating a new key dynamically on the fly for, say, a driver or for this new page table use case was going to be kind of difficult, because we would want to get the default to be read only and not access disable. And after going through a number of iterations and trying different things and trying to basically update all current users, we just abandoned the dynamic allocator. Since we only have 2 use cases and kind of a third in the wings, and we have 15 keys, static key allocation just seemed like a better way to go at this time. We don't really anticipate that the numbers of users are going to grow a lot. And the other thing is that even if the number of users grew, the sharing of a single key would have to be kind of worked out, and that probably would need to be worked out, you know, as the software was being designed, rather than something that could be done dynamically. So real quick on the right side, a little bit of use of how you use this interface. We you know, we have an enum that defines all the consumers for P keys. You know, in this case, I've got my feature, and you know, I can add the default value for my feature. As we can see, the default key, which is key 0, is basically complete read and write access. My feature has a disable write feature, you know, and there's an access disable default as well. So another thing that is very obvious from the thread local and Xsave not being supported is the fact that threads and exceptions need to have the MSR cached away as things are scheduled in, scheduled out, accepted, interrupted. So initially we knew right away we were going to have to do this for threads. So we added a cached MSR to the thread struct. You know, I mentioned earlier that we did do some optimizations in the software to not update the MSR if we don't need. So if a thread is scheduled in and the MSR hasn't changed, it can just continue running without updating the MSR. So the overhead there is pretty quick. Initially, we just skipped exception save support. It was kind of decided that, especially for stray write use case, you know, having little windows where an exception would have access if it accepted a critical section of the persistent memory users, that it would be fine for that exception to be able to have access. But as Rick's use case came online, and other use cases like the potential to try to protect you know, any kernel secrets, we started to say, you know what, we really should support exception save support. And with exception save support, we initially looked at using the IRQ save structure. And you know, when we decided to go ahead and add exception save support, it looked like the IRQ save structure was going to be pretty easy. We could just kind of cache the MSR there, and you know, recursively, if an exception got accepted, we can just kind of update that cached value, and you know, kind of recurse down, and it wasn't really going to be that hard to do. But a lot of people didn't like that. The patches were pretty complex. We had to add that structure to be passed around to various places to make sure that, you know, anybody that needed that MSR value could have access to it. And eventually, Andy Lutromirsky, I hope I'm pronouncing that correctly, came up with a clever little idea to, you know, throw a little extra stack space in, kind of in a, you know, extra stack space that's not there, and extend the PT register structure. So, you know, it was batted around to add this to the PT reg structure, but the PT reg structure is somewhat public, where people need that structure to be well defined for things like BPF. And so we really didn't want to touch the PT reg structure. But Andy's idea was to just throw a little bit of stack space in there and extend that register so that we can get to that pointer only if we need to. And that was really clever. And I like the idea, but, you know, coming from, you know, a driver writer standpoint, and I haven't worked on assembly code in probably 20 years. And when I did, it was PowerPC assembly, you know, opening up the entry code and looking in there on those files, it was pretty daunting for me. But, you know, I dug in and asked a lot of questions, and I believe the patch set that we have actually implements it relatively nicely. And so that's pretty clean. So anybody that has a PT reg struct, and we went ahead and added that extra space and cached the MSR in all the exception entry points, not just the ones we thought we would need, you know. So, and there is a little bit of extra space because we only needed 32 bits, but we went ahead and added 64. And so that allows a little bit of space there. And so anybody that has a PT reg struct can just get to that cached MSR. So Now, to get back to the relax mode, this is another thing that, our use cases really helped to drive what our core support needed. Like I said, initially, I really tried to implement something that did the fault handler and change the global value of all the MSRs if that KMAP call was called. And, like we said, from the discussions, we said, hey, if you update that globally, then effectively you're turning off permissions. It's not a big deal. So we kind of discussed having a relaxed mode. Initially, it was suggested that we have a relaxed, a silent, and a strict option, where silent was basically doing the same thing as relaxed, allowing the system to continue running, but not actually print any warnings. We decided to drop that because really the point is we want people to know that a stray write occurred. In my case, a stray write occurred, and in Rick's case, that somebody actually tried to update the page tables without doing the correct access. So we just have a relax and a strict mode. And in doing this, I was focused on people trying to do KMAP. So the KMAP actually tries to flag this relax mode right away, tell people where that KMAP occurred. And I decided to drop the fault handling code because it was complicated and I wasn't going to try to do an update to the global. But the problem is with Rick's use case, there was really no way to do a relax mode without the fault handling code. And so he revisited that, and I'm going to let him talk to this next slide because he ended up implementing what is currently submitted upstream.
Yeah.
So I can just flip the slide. Yeah. Okay. Thanks.
Okay. Yeah. So the problem is that the kernel, there's been a PKS fault, and how can the kernel know what to do? If you only have one PKS usage, this is a little simpler. But now if you have two, you have to know, should we should the kernel disable protection? What message should it print? In order to decide any of that, it needs to know which key. But the only PKS information the fault handler gets is that the fault is due to a protection key violation. There's an error code bit, a page fault error code bit. It doesn't find out which key caused it. But the keys in the page tables in the kernel does have the address that caused the fault, so it has to walk the page tables to get the protection key. That's the only way it can know which, well, I shouldn't say the only know, anyway. That's the only way that we looked at it can know what type of violation this is. This can be a bit tricky because the kernel could be an interrupt, so taking locks, it takes extra consideration. And the special worry is that a kernel page table could be freed while the kernel is walking, and then it could start walking random memory. And talk about how for the PMEM usage, the threat model, or not threat model, like the bug model is that a stray access could happen from some other bug in the kernel, and we want to make sure it doesn't cause problems. And so the expectation for the soft mode is that it won't cause problems. And so we sort of need to handle, making sure we handle that well. The special worry is that a kernel page table could be freed, while the kernel is walking, and it could start walking random memory. But luckily, the kernel memory page tables and the kernel half of the address space are not freed very often, but it does happen. So I looked at how we could maybe deal with this, and this is an idea that we were tossing around in the diagram here. It's pretty self-explanatory, but not quite clear how much we need to worry about this, because there are other page table walks in the kernel that don't take this into consideration. So not sure whether, since we're sort of worrying about the case that we're worrying about the case of like bugs, we're sort of our use cases that a bug exists. So how much we should maybe worry about extra things going wrong or not. Right now, we're not doing anything special around this. We're just walking it like the other walks in the fault handler do. But still sort of considering whether we should need to do this or not. Okay, back to you, Ira. Ira?
Yeah, go ahead and flip the page.
Okay.
Oh, I'm sorry. Thank you. Sorry about switching back and forth.
Oh yeah.
Oh, no problem at all. Sorry, I wasn't fast enough this time.
No, that's okay. We actually discussed a lot about, you know, how we're going to switch back and forth, try to make it more efficient. So we've kind of come back around to our status and next steps. You know, obviously some of the core software has changed with our use cases, which, you know, I think is a really good thing. You know, I think it's made the core more robust. Very quickly, our use cases are posted, and the core was posted along with the initial PMEM use case. Version 7 of the patches are now upstream. If people are interested in how this feature works, at least currently with the core, it is documented under protection keys in the documentation part, and that was modified in that patch set to include the users, I'm sorry, not the user space, the kernel space protections. And the page table support is currently in RFC v2, and there's the link there for that for people who are interested. Another thing is that if you want to test this or play with it, it is supported in QEMU. So, you know, this is the option to use for QEMU. And like I said, I did have a test slide, but I dropped it. The core patch set does include a patch that implements tests, and I have actually used it quite a bit to do regression testing and to actually test some things out. I'm sorry, but Paul's previous talk just, you know, really kind of influenced me, because writing those tests really did, I think I hit on maybe every point that he made about, you know, the test failing but not failing, or showing success when it really wasn't working. And anyway, it's interesting. And the next steps for the PMEM use case are to I would like to continue to remove the KMAP users. You know, generally the kernel community has said we don't like KMAP. At least the current implementation of KMAP, the KMAP local page is fine. And so I want to continue to remove those. And eventually, once I remove those, I think we could, you know, and we see some runtime out in the wild, you know, we can go ahead and make that restricted or fault mode back to strict instead of relaxed. So that we, you know that users are actually fully protected. And then for the next steps for the page table, go ahead, Rick. I don't know if you want to talk to this slide.
Yeah. Yeah. So like I mentioned earlier, the this PKS tables usage is in a lot earlier of a stage than the PMEM usage. Still kind of exploring it out. So right now, what we've got is sort of it's functionally, you know, I should say it's not ready for upstream functionally, but it's, you know, we've checked all the functional to-dos. We protect all the known page tables, although that's just virtual page tables. It doesn't do EPT or IOMMU. It handles the direct map issues with the solution I described earlier, and it has the soft or relaxed mode, as we're going to start calling it, so we can call things the same name, so that you know, if there's you know, we're applying this new protection, this new rule on top of code that was written, not assuming it. So just take an extra bit care there. So the next plans, the plans going forward are around exploring performance and tuning. The main thing I think we have to play with is how many page tables we convert at once. So that'll reduce breakage and amortize the shoot downs better. And then also Mike Rappaport started actually took the first RFC and built a new sort of a new exploration of how to handle permission pages on the direct map, which looked at putting in the page allocator. And so he's apparently going to continue working on this. And so this PKS tables usage would be a happy customer of that component. If something can be, if we can end up with something. And just a little plug, tomorrow there's a BOF session on direct map permission stuff. So if you're interested in discussing it, please come by. Back to you, Ira.
Yeah, I think it's pretty obvious from the chat session that your use case is the one that, is still very much in discussion.
Yeah, it's a lot
Just
earlier.
looking at, looking at the number of people talking, people are like, yeah, straight right, whatever, go protect your PMEM. We don't care about you. Talk about the page tables. We care about those. Everybody cares about those. And I agree with that. I think, no offense at all, Mike. I think this is I think this is part of what this discussion's for. It's one of the reasons that I really wanted Rick to kind of to jump in with this conversation, because I think it's I think it's great that we're seeing more use cases for this core support. I think it's great that he fed he fed requirements back to me into the core. Our last slide here is just acknowledgements. People, Dave is jumping in on the chat here. Dan Williams with the PMEM and everything, the reviews that have happened. Obviously Andy and Thomas have had a lot of input. Peter, Sean, Christoph, and Funghua actually implemented the initial core support in version 1 of the patch set that was submitted upstream. So, all these people have had input into this patch set and this feature and discussions. So, actually, we really should have put Mike on there too. Mike has really had a lot of input with the with the page table side of things. So thank you, Mike Rappaport. Am I pronouncing that correctly, Mike? You can just chat. And if you want, we've got 5 more minutes, and I think we're the last talk of the day, so we could even just open it up to people speaking if they wanted.
Yes, sure. If you if someone wants to ask questions, please turn on the camera and audio. We prefer if questions are asked live, not just in the chat. Gives it more the feel of an actual conference.
I have to say, I didn't attend this last year. This year, everything, it's very nice. It actually does have a pretty good feel of a real conference. So anyway, a shout out to all the organizers.
Thank you.
Yeah, I kind of like the sidebar chat. It could be a nice feature of an in-person conference even. So people are on their laptops or something, could be have a little silent chat room.
So I've been trying to when Rick was talking, I've been trying to read this and discuss this. I think the initial question was, could this be done with regular page table permissions? And like I said earlier in the talk, the PKS does layer on top of the page table permissions, and so technically, I think it is possible. I think Dave and I both answered that, but Dave, there's been a long discussion I haven't quite fully followed, but I think that the issue is that it's just harder to do with the page table permissions. And I really think this is a cool feature where you can kind of set this domain, and we can say all page tables are part of this domain that can be turned on and off, just like I'm doing with persistent memory. Dave, you wanted to say something?
Yeah, I would love to see this, like the general idea of page table protection. I would love to see it implemented with more, other pieces of hardware. Page tables are one of them. Like, it'd be also fun to do this with hypercalls. We could actually ask the hypervisors to do this stuff for us. So that'd be a cool thing to do too. So and you could do that. Yep. So there's a lot of options here. So if people have other ways of doing this, I'd love to hear it. The other thing is this hardware right now, I don't think we have any publicly available hardware that does PKS. So you probably get more interest when that happens. But we really hope this shows up across a lot of CPUs, including all the way down to everybody's laptops. So maybe in a couple of years, people will be a little more interested when it's on everyone's laptops.
Yeah, I really wanted to say something about which CPUs, but the current software development model, I'm sorry, the SDM says future CPUs. So yeah.
It is in QEMU though. If anyone, I think we have a slide on that. So if anyone wants to try this, or if they have an idea for another thing in the kernel that could use quick toggleable protection, this works pretty well. So you can give it a try. You're not going to get the performance benefits, but for development.
Yeah, I think what Dave just said is really, yeah. So So Keys says, I want to protect against stray writes, but I want to protect all memory. Well, I you know, yeah, you know, technically, you know, from a technical standpoint, that's really easy. All you got to do is change p key 0 in the current implementation to be, you know, read only or whatever. But I think you would break a lot of places, because the key is that you have to allow users access. So you still need to, I think you still need to create the different classes, domains of memory, to be able to allow access when it's intended.
For code patching, one thing I was sort of wondering about is if we could have kernel page read only be a protection key, so that we apply a protection key to basically, instead of using the read only, the read write bit in the page table, we would use a protection key to apply the read only to text, and then you could just sort of patch it in place. I haven't fully thought that out, but you know, someone mentioned in the chat about text patching, and it might be a small change. I did wonder though how much people are wishing text patching was faster. I'm not sure.
Yeah, I don't know. Yeah. James wants a pony too. Yeah, I want a pony. Let's see here.
There
XPFO.
is still, oh, sorry, go on.
No, Dave mentioned XPFO. That's something else we've investigated internally. I looked at that a while back. I forget the details on it though. But yeah, that seemed like it might be a good use case for this. Just generally from what I remember.
Yeah.
But I don't remember the details. It's been a while. I'm really focused on getting this core support upstream, and then we can kind of, you know, build on top of it. So. And technically, I work on the persistent memory team here, so technically my driving factor is really the persistent memory stuff. But I think, like lots of people, you end up running into memory management code and needing to update it and make sure it's correct. Only open the permissions. So Mark Rutland, you said something about you only open the permissions on the CPU performing the text poke. I'm not sure what that was in reference to.
I think the point there, Ira, was that when you're doing a text poke, there's really only one CPU that's writing to that piece of text that you're trying to modify. But that writable page table entry is visible to everybody in the kernel. And so in theory, a stray write from somebody else in the kernel could come and use that page table entry. So if you use PKS for that, in theory, you could do something where only the CPU doing the text poke had access to that writable entry.
Okay, yeah. So this is what Rick was talking about earlier.
Yeah, on x86 though, it uses the temporary MM to do a per CPU mapping.
Right.
Oh, that's a good point. It's the textbook MM, isn't it? Yeah.
But of course, the memory that's about to be copied is visible everywhere. So, you know, the attacker could just target the other memory that's about to be copied. Well, I shouldn't say could just do it. It gets more complicated, but.
So is that temporary MM CPU local? Like,
yeah.
That's okay. So that's been my confusion over whether or not we were actually using per CPU page tables, is because we sort of have this half state where that exists.
Yeah, it maps it in not in the kernel address space. Is how it works. I think more than x86 uses it now. I think I saw some other architecture was turning it on.
I thought power might be, but
yeah.
So two CPUs don't end up with the same area that they can write to then?
That's the design.
Okay.
Like native emit did that stuff.
Yeah, and it kind of takes the user space approach because user space has an MM and we actually have a whole MM just for text booking. So it's a kernel only one. It's kind of like an NVDIMM, but yeah, I totally forgot about that case. I hope I didn't mislead you too long there.
Well, it's just, I mean, it's not strictly a per CPU page table, like I get that, but I mean, it is an interesting approach to being able to perform writes that are CPU, only visible to that CPU.
But in Rick's case, you want that to eventually get to everybody else. Whereas with the text poke, I think you want it to remain local, right?
Well, the writing permission I want to keep local. The result of the write will eventually be visible to everybody.
And so is that text poke MM visible eventually to everyone?
No.
Yes.
Yeah, the write is visible. So it creates an alias basically, but a per CPU alias.
So we could, for instance,
Right.
keep 2 copies of the page tables, one of which has a read-write copy of the page tables, like just like we have now, and then one other, top-level PGD that has read-write page tables. We could keep 2 of them in parallel, right? This would get nasty for other reasons, but we could keep 2 of them, and then instead of doing a PKS write when we're trying to toggle permissions to the page tables, we could just do a CR3 write to switch between the 2 copies. That's an option too.
Sure. Yeah, okay. Go ahead, Mike. You popped up a couple times.
I wanted to comment to Dave's remark about having the entire MM for a single page table. I looked at some point at having a proper kernel page tables without the MM, and not sure it's worth the churn because anyway we will have to convert at some point, and it would be too intrusive, I think.
Yeah, maybe. Who knows? We got to try it. It might be horrible, but might not be too bad.
I mean, if there are no more questions, then we can surely close the session. If you want to continue discussing, I'm sure we can leave the room open for a few more minutes. But other than that, this was the last talk in the Refereed Track for today. It was really great. Thank you everyone for being here, and good evening, good afternoon, good morning, I guess.
Thank you.
Thank you.